Out beyond Neptune, where sunlight is a rumour, our telescopes keep catching a faint infrared whisper, coming from the exact patch of darkness where Planet 9 should be. The math says whatever's hiding there could be 10 times Earth's mass, so are we finally hearing a secret planet, or the signature of something far worse, a primordial black hole rewriting the edge of our solar system? In the farthest ledger of our solar system, gravity keeps records, and lately the entries no longer balance. What should be random is beginning to look arranged, as if an unseen hand has been editing the margins. Neptune is not a border so much as a last familiar landmark. Beyond it, the map turns to inference. Out there, objects take millennia to complete a single loop, and our telescopes catch only brief, biased glimpses. Yet those glimpses carry geometry, and geometry carries memory of tugs, talks, and long, patient shepherding. This is a story about evidence that refuses to stay neatly separated. A few distant worlds trace paths that seem to rhyme in their angles, even when time should have erased the pattern. A handful of photons in the infrared arrive with the wrong kind of persistence, hovering near the threshold where galaxies, cirrus, and instrument artifacts can masquerade as discovery. And with every new orbit measured, the corridor of possibility narrows, then shifts again, like a door seen through heat haze. To chase a hidden mass at the edge of the sun's reach is to fight physics itself. Light falls away by the inverse square law, motion slows until it looks like stillness, and the sky becomes a crowded field where almost everything is a false positive. So the hunt becomes a discipline of restraint. Repeat detections, parallax, proper motion, and the hard accounting of selection effects. The most unsettling prospect is not danger, but misinterpretation, that our instruments are correct, and our intuition about what belongs in the solar system is not. In the chapters ahead, we will step from dynamics to photons and back again, following the trail in both directions. We will meet the extreme trans-Neptunian objects whose orientations act like compass needles to a distant source. We will sift the infrared sky the way auditors sift a balance sheet, asking what kind of body can hide in plain data. We will weigh a new arrival in the catalogue, 2023 KQ14, like a witness whose testimony could steady the case or fracture it. And we will confront an alternative that is colder than any planet, because it may not shine at all, a compact relic of the early universe, detectable only by the gravity it cannot help but exert. Soon, the search changes from a handful of hard-won detections to an industrial cadence of sky coverage. The Rubin Observatory will not merely look deeper, it will look again and again, turning time into an instrument. In that repetition lies the difference between rumour and measurement, between a suggestive alignment and a quantified selection function, between a candidate source and an orbit you can close. What follows is an exploration of how scientists read the outer solar system, how they separate pattern from bias, signal from noise, and hope from statistical mirage. And as the data tighten, the question stops being whether something is out there. It becomes what kind of thing could leave these fingerprints, and why the solar system kept it secret for so long. Before we begin, let us know in the comments below where in the world you're watching from and what time it is there. Now, settle in for a journey. We will travel from orbital oddities to infrared catalogues, then into the stark logic of black hole alternatives, before the Rubin era forces a verdict. By the end, the edge of the solar system will feel less like emptiness, and more like an archive waiting to be decoded. The solar system feels vast until you measure it against the galaxy's dark ocean. Our planets seem spread out on diagrams, yet they occupy a tiny coastal shelf of the Milky Way. Even our farthest worlds orbit inside a thin bubble of sunlight and habit, an atmosphere of influence that fades, not with a wall, but with a gradient. Past that bubble, distance stops being a number and becomes a barrier. Light weakens by the inverse square law, so every extra step outward steals contrast from the things we hope to see. Time also stretches in a practical way, because an object taking millennia to orbit barely shifts in a human lifetime. In wide shots, the sun becomes a bright pin, and the outer system becomes a dim, slow choreography. Neptune marks the last bright landmark most people can name with confidence. In telescopic images, it's a small blue disk, but in the mind, it is a border. Beyond it, the map turns grainy and incomplete. The Kuiper Belt begins as a broad ring of icy debris and dwarf worlds, a reservoir of leftovers from planet formation. Its members are not just rocks. Many are mixtures of water ice, methane, and complex organics darkened by radiation. Farther out, the scattered disk stretches into elongated, tilted paths that barely return. These objects were likely kicked outward by Neptune's gravity long ago, then left on orbits that skim the Sun and retreat into deep cold. Some are so detached that they rarely feel Neptune at all, as if they belong to a different system. On screen, their orbits look like thin, pale loops, crossing and tilting like threads in a black loom. Voyager 1 and Voyager 2 did not explore these regions in detail. They raced outward on narrow trajectories, sampling only a few points in a huge volume, like needles passing through fog. Their instruments hinted at changing particle environments and thinning solar influence, including shifts in plasma density and magnetic field structure. They also reminded us how little we can touch, even when we can fly through. The Voyager's journey carries a historical weight that is easy to forget. They launched in the late 1970s, when computers were weaker than modern phones and deep space navigation was an art of patience. Their famous planetary encounters were brief, because speed was the price of reaching the frontier at all. Past the bright planets, they became messengers of absence, reporting not what is there, but what is no longer dominant. This chapter starts with a premise that sounds like fiction, but is built from math. The horror is not monsters or aliens, and not a radio voice from the void. The horror is the possibility that our own solar system still hides a major object, far beyond Neptune's light. If that is true, our map has been wrong in a fundamental way. A hidden planet is unsettling because it changes what we think is stable. It changes how we model the past and how we predict the future, because gravity integrates over time like interest. It changes what counts as a safe neighborhood around the Sun, even if the danger is only conceptual. It also forces a question that science hates to ask twice. How did we miss something big in our own backyard? That question has precedent, and it echoes through astronomy's history. Uranus was found in 1781, not because it was invisible, but because it was mistaken for a star until motion gave it away. Neptune itself was predicted from orbital irregularities, a triumph of inference before direct sight. Pluto followed as a different kind of story, discovered in 1930 and later reclassified when the Kuiper Belt revealed it as one among many. The modern Planet 9 story begins with small bodies, not a giant world. Astronomers track trans-Neptunian objects, or TNOs, by catching faint points of light over many nights, then linking them into a coherent path. Each detection is a photon budget problem at the edge of instrument limits, where noise and sky brightness compete with the signal. From those points, they fit orbits and estimate where the object has been and will be. In plain language, an orbit is a repeated path shaped by gravity. In practice, it is a set of parameters, inclination, eccentricity, perihelion distance, that encode a history of past nudges. If many distant objects point their closest approach in similar directions, that is not expected by chance. If their orbital planes tilt in related ways, that is another clue, because random kicks should smear them out. Alignment like that suggests shepherding, like a heavy hand guiding lighter debris. In celestial mechanics, a massive body can trap smaller ones in resonances, or slowly torque their orbits through long-term secular effects. These influences are subtle, but they accumulate over millions of years until a pattern becomes visible. The outer solar system is a laboratory where time is the dominant force, and patience becomes a scientific instrument. The key claim is simple and controversial. Several extreme TNOs have orbits that appear oddly aligned in space, as though their long axes share a preferred direction. Their perihelia cluster, and their orbital orientations seem to point together, even though they are separated by enormous distances. The farther and more detached the objects are, the harder it is to blame Neptune's direct influence. Scientists argue about whether the alignment is real or an artifact. We discover TNOs with telescopes that scan certain parts of the sky more often, and those choices are shaped by season, weather, and the geometry of Earth's orbit. We detect brighter objects more easily, and brighter often means closer or larger, which skews what enters the catalogue. Those biases can create patterns that look meaningful until you model the selection effects. There is also a human bias built into the hunt, even when no one intends it. When a survey finds an object, follow-up observations tend to focus where it is easiest to recover, not where it is hardest. That practical constraint can reinforce an apparent clustering, because the sky is not searched uniformly. In a field built on faint dots, the difference between not there and not yet found is a philosophical fault line. Still, the pattern has refused to die, and that is why it matters. With each new survey, the question returns with better statistics and sharper arguments, and the uncertainty narrows in uneven steps. The debate is not only about a planet, but about how we infer unseen causes when we cannot run experiments. It is a test of how astronomy works when the data are scarce and the priors are contested. From this tension, the phrase signals enters the story, and it needs a clean definition. These are not radio messages and not deliberate beacons, because the outer solar system is quiet in that way. They are faint infrared detections and candidate sources from wide-field sky surveys, often buried among countless background objects. They are photons arriving from the dark, carrying heat signatures or reflected sunlight re-radiated as warmth. A cold, distant planet would be dim in visible light, because sunlight is weak out there. At hundreds of astronomical units, the sun is not a blazing lamp but a bright star, and the reflected light drops to a whisper. But the planet would still emit thermal radiation, because all objects with temperature glow, even if that glow peaks at long wavelengths. In infrared, a large body can stand out against the background if you know where to look. The problem is that the background is crowded and the motion is slow. Distant galaxies, dusty star-forming regions, and faint brown dwarfs can mimic the colours of a cold planet in certain filters. The sky also contains instrumental artifacts, glints, noise patterns, and calibration ghosts that look real until they fail a second test. A true solar system body should move, but at extreme distances that motion can be tiny over months. When astronomers say a candidate, they mean a source that looks plausible but is unconfirmed. It might be a distant solar system body, or it might be a galaxy, a brown dwarf, or an artifact that only exists in one pass. Confirmation requires repeated detections and measurable motion against the stars, ideally with different instruments and at different times. In the outer system, even parallax from Earth's orbit becomes a subtle ruler. The unsettling hook is that some infrared candidates sit near where Planet 9 should be. Not exactly on a single predicted dot, because predictions are broad and model dependent, and they depend on which TNOs you trust. But within the regions where orbital fits say an unseen mass could hide, a few sources linger like unanswered questions. That overlap is the whisper, and it is why the story feels like a hunt. The stakes are bigger than one extra planet in a textbook diagram. If Planet 9 exists, it reshapes models of solar system formation and migration, because a several Earth mass body does not appear without consequences. It could explain why some objects are detached and tilted, and why certain inclinations seem overrepresented. It could connect our system to the dynamics seen around other stars, where super-Earths and distant companions appear common. If Planet 9 does not exist, the stakes are still enormous. Then our statistics may be fooling us, or our survey biases are stronger than we admit even after careful modelling, or our dynamical assumptions are incomplete at the solar system's edge, where weak forces act for very long times. In that case, cosmology meets local astronomy in an uncomfortable way, because the error is not in the sky, but in our interpretation. The numbers behind Planet 9 are both specific and flexible. Many models suggest a mass several times Earth, perhaps up to 10 Earth masses, which would place it between Earth and Neptune in scale. The orbit would be long and stretched, taking thousands of years to circle the Sun, with a perihelion still far beyond Neptune. Its distance could be hundreds of astronomical units, far beyond Neptune's 30, where sunlight is diluted to a pale wash. Such a body would be hard to see, but not impossible to infer. Gravity leaves fingerprints even when light does not, and those fingerprints appear as long-term sculpting rather than sudden disruption. It shapes the distribution of small bodies over millions of years, nudging some into aligned configurations and pushing others into high inclinations. It can also pump eccentricities and create resonant patterns that persist, like grooves worn into a record. The first thread we follow is orbital evidence, often summarized as 6 frozen worlds and more. A handful of extreme TNOs became the original dataset for the alignment claim, and each had to be tracked across years to reduce uncertainty. Later discoveries added complexity, sometimes strengthening the case, sometimes weakening it as new orientations filled in the map. The core question remains whether the clustering is statistically robust, or whether it dissolves as the sample grows. On visuals, these objects are not seen as worlds with horizons, but as plotted arcs on a black field. The camera can glide along a diagram where perihelia bunch like compass needles, then pull back to show how sparse the detections really are. Each orbit line represents years of telescope time, careful astrometry, and the quiet labour of linking observations. It is a reminder that the outer solar system is not empty, but it is undercounted. The second thread is infrared candidates, including work tied to the Akari survey. Akari mapped the sky in infrared and produced catalogues of sources, a kind of thermal atlas that complements visible light surveys. Researchers can mine those catalogues for objects that move slowly and match expected colours, then cross-check them against other data sets. A candidate is only a starting point, but it can focus attention, narrowing a search from the whole sky to a few tense patches. Infrared work also forces a practical question. What does cold mean in space? At great distances, a planet's temperature depends on its internal heat as much as sunlight, because residual formation energy and slow radioactive decay can keep it warmer than the environment. That warmth changes the expected brightness in infrared, and it changes which instruments have a chance. The hunt becomes a negotiation between physics and technology, between what might exist and what we can detect. The third thread is new dynamical clues, including the object designated 2023 KQ-14. New objects matter because each orbit is a new constraint on the unseen sculptor, and constraints are how hypotheses survive. Some discoveries appear detached in ways that are hard to explain with known planets alone, especially if their perihelia stay far from Neptune's reach. Others test whether the supposed alignment persists as the sample grows, or whether it was a statistical mirage. These threads do not guarantee a planet, and the documentary must keep that uncertainty honest. Planet 9 is a hypothesis built from patterns, not a photographed globe with clouds and weather bands. The evidence is indirect, and indirect evidence can be powerful or misleading, depending on how well alternatives are excluded. The tone is wonder, but the method is skepticism, because the universe rewards the careful, not the eager. There is also a fourth idea that turns the story from unsettling to truly strange. Instead of a planet, the hidden mass could be a primordial black hole, not a stellar black hole made by a dying star. It would be a compact relic from the early universe, formed from density fluctuations before stars existed. It would be tiny in size, perhaps grapefruit-sized, but massive enough to shepherd orbits, because gravity cares about mass, not diameter. A primordial black hole would not shine like a planet, and it would not reflect sunlight. It might reveal itself through gravitational effects and rare interactions with surrounding material, such as brief accretion events that produce faint radiation. It could also produce subtle signals if it accretes dust or emits Hawking radiation in speculative regimes, though that remains uncertain. The point is not that it is likely, but that it is allowed by some models, which makes the mystery deeper. This alternative matters because it reframes what we mean by discovery. If the unseen mass is a planet, we add a new member to the solar system family, and we revise formation stories accordingly. If it is a black hole, we add a piece of the early universe to our local neighbourhood, a fossil from a time before atoms cooled. Either way, our sense of what is nearby becomes less comfortable, because nearby stops meaning well-known. The broader universe context is not decoration, it is the reason the hunt is credible. We now know planets are common around other stars, and many systems are stranger than ours, with hot giants and compact chains. We also know our solar system has a violent past of migration and scattering, recorded in craters and resonant populations. A hidden world beyond Neptune would fit that theme, even if it surprises us, because the outer system is where leftovers keep secrets. NASA's discovery culture shapes how this story is told and tested. Big surveys, open catalogues, and competing teams create a fast feedback loop where claims are checked by rivals with different methods. Data are reanalyzed, biases are debated, and simulations are rerun with new assumptions and larger samples. The energy feels like a top mysteries countdown, but the process is slow and technical, and the suspense comes from rigor, not spectacle. The phrase horrifying planets needs one more careful framing. The fear is not that a distant planet will suddenly attack Earth, because gravity at those distances is not a sudden weapon. The fear is epistemic, the realization that our inventory is incomplete even in our own system. When the solar system's edge becomes uncertain, certainty elsewhere feels thinner, and the comfort of a finished map disappears. At the same time, the story is not nihilistic. And it is not paranormal. The tools are telescopes, catalogues, orbital fits, and simulations, plus the patient arithmetic of error bars. The language is probability, bias, and dynamical stability, translated into plain speech when it needs to be. The drama comes from how little light there is and how much inference we must do, while knowing that nature owes us no tidy answer. So we begin at the boundary where sunlight becomes a rumour and time moves differently. We listen for an infrared whisper in a cold sky full of false positives, where a galaxy can impersonate a planet. We watch small worlds trace long arcs that hint at a heavy companion, and we ask what kind of companion could hide so well. Then we ask the central question with no comfort built in, because the frontier is not just far away, it is unfinished. Are the infrared signals and the strange outer orbits evidence of a real Planet 9, or are we seeing something far stranger? A compact dark mass reshaping the edge of our solar system. The next chapter follows the first thread, the orbital evidence, and tests whether alignment is a clue or a mirage. Neptune is not the end of the solar system. It is the last bright marker before the map becomes statistical, where objects are inferred as much as they're seen. Beyond it, the Kuiper belt and the scattered disk hold bodies that barely shift against the stars in a human lifetime. Their faintness is not only distance, but also geometry, because we detect them best when their orbits bring them closer. Out there, sunlight arrives diluted by the inverse square law, and the sky becomes a place where a small change in distance means a huge change in brightness. A world twice as far away is not twice as dim. It is roughly 16 times harder to see in reflected light. That harsh scaling is why the far frontier feels empty in photographs, even when it is not. The photons are real, but they are spread thin. Each square meter of telescope mirror collects only a whisper from the sun's leftovers. The camera can linger on a familiar diagram of the solar system, then slowly zoom outward until the neat planetary lanes dissolve into a thin haze. The inner planets become a bright knot. The outer planets become tick marks. Then even Neptune becomes a dot, and the rest is mostly empty black. In that black, the mind wants landmarks, and science has to build them from motion. A distant body is not announced by a blazing disk, but by a slow drift that repeats, frame to frame, night to night, season to season. Chapter 1 asked why an infrared whisper overlaps the predicted hiding place of a massive perturber. Chapter 2 narrows to the orbital evidence that created that prediction. The evidence begins with a small set of extreme trans-Neptunian objects, bodies whose paths look less like ordinary Kuiper belt loops, and more like long, stretched signatures. They are not planets in the cinematic sense. They are frozen time capsules whose orbits preserve the solar system's gravitational history. A time capsule is not valuable because it is big. It is valuable because it is undisturbed, and because it carries the imprint of forces that acted when the solar system was young. In the outer solar system, undisturbed has a technical meaning that is easy to miss. It means an orbit that avoided repeated close encounters, avoided collisions, and avoided the slow erasing effect of constant gravitational stirring. These bodies are sometimes called extreme TNOs, or detached objects, because their perihelia sit far enough away that Neptune cannot easily grab them. They spend most of their time far beyond Neptune, then briefly return to the inner edge of our reach. Their long periods mean each orbit is a multi-century or multi-millennia statement. That statement is written in orbital elements, not in rock. A distant object can be only a few hundred kilometers wide, yet its trajectory can encode billions of years of dynamical history, like a fossil that records climate without preserving a single leaf. In practice, we discover them during the brief portion of their lives when they're close enough to be detected, and that fact shapes everything. A distant object can spend 99% of its orbit in deep darkness, then become visible for only a narrow arc. The catalogue, therefore, is built from rare moments. Those moments are not evenly distributed across the sky. They happen where an object's orbit brings it near the Sun from our perspective, and where Earth happens to be when we are looking, an observational geometry that quietly edits the story we tell. The story often begins with 6 names, because 6 early orbits look too coordinated to ignore. Sedna is the famous one, a reddish worldlet discovered in 2003, with a perihelion far from Neptune's direct control. 2012 VP113 joined it as another detached world with a similarly distant closest approach. Sedna's orbit is so elongated that it spends most of its time in a realm where the Sun is just another bright star. Its surface colour hints at complex organics altered by radiation, and its extreme perihelion raised an immediate question: what lifted it so high? Then came objects like 2010, GB174 and 2004 VN1-12, each with large semi-major axes and high eccentricities that carry them far into the cold. 2013 RF98 and 2007 TG402 entered the discussion as additional extreme examples with comparable orbital scales. The exact roster shifts by paper and by updated orbit fits, but the core claim stays similar. For visuals, these names can appear as small labels on a black field, each attached to a faint ellipse that stretches outward like a pulled thread. The ellipses do not overlap as a cluster of bodies, they overlap as a cluster of directions. A subtle visual detail helps here. When the camera rotates the scene into 3 dimensions, the ellipses separate in space, yet their long axes still seem to agree, as if several arrows were laid down with similar bearings. These are not the only distant bodies. They are the ones whose perihelia are high enough and whose semi-major axes are large enough to make Neptune an incomplete explanation. Neptune is powerful, but its power has a reach. If a small body's perihelion stays too far away, Neptune's gravitational kicks become weak and infrequent, and the orbit can remain detached for billions of years. That reach is not a hard wall, but it is a practical boundary. Gravitational influence fades with distance, and the timing of encounters matters. An object that never comes close never gets the kind of chaotic reshuffling that sculpts the scattered disk. To understand the claim, the audience needs a clean set of orbital terms, because the argument is built from geometry. An orbit is not just a loop. It is a set of parameters that encode distance, tilt, and orientation in space. Perihelion is the closest point to the Sun, the moment when the object is warmest and brightest, though still unimaginably cold. Aphelion is the farthest point from the Sun, where the object moves slowest and spends the most time. The semi-major axis is the orbit's average size, the number that sets the period through Kepler's third law. Kepler's law is simple in plain language. The bigger the orbit, the longer the year. In mathematical form, the period squared scales with the semi-major axis cubed, which means time grows quickly as distance grows. At a few hundred astronomical units, a year becomes a human history. An object can take 1,000 years to return to the same place, and our entire era of telescopic astronomy covers only a thin slice of that path. Eccentricity measures how stretched the orbit is. A circle has eccentricity near zero. An extreme TNO can have eccentricity so high that it lives in deep cold and only visits the Sun's outskirts. A helpful visual is a circle beside a long ellipse, with the Sun offset from the centre, because the Sun sits at a focus. That offset matters, because it creates a dramatic difference between perihelion and aphelion distances. In that ellipse, speed is not constant. Near perihelion, the object is moving fastest, and near aphelion it crawls, Kepler's second law in action, a reminder that gravity shapes time as well as space. Inclination is the tilt of the orbital plane relative to the solar system's main plane. The main plane is defined by the planets, especially the ecliptic traced by Earth. High inclination means the object spends its life above and below that familiar flat diagram. In animation, the ecliptic can be a thin glowing disk, while a tilted orbit slices through it like a ring set at an angle. The object itself is a speck, but the geometry is the point. 2 other angles matter for the alignment claim, and they are easy to misunderstand even for careful listeners. The argument of perihelion tells where perihelion sits within the object's orbital plane. The longitude of the ascending node tells where the tilted orbit crosses the reference plane going north. Together, these angles define the orbit's orientation in 3 dimensions. They tell which direction the long axis points, and which side of the Sun the closest approach occurs. They do not mean the objects are physically near each other. When people hear aligned orbits, they imagine a row of bodies lined up in space like beads on a wire. That is not the claim. The claim is clustering of orbital angles, meaning several long axes point in similar directions, and several perihelia occur in similar longitudes. A good visual is to show 6 elongated ellipses around the Sun, each one tilted differently, but with their closest approaches pointing roughly the same way. The bodies are scattered along those ellipses far apart in space and time. The alignment is in the arrows, not in the dots. If the outer solar system was stirred only by random kicks and the known planets, those angles should be scattered. Over billions of years, repeated perturbations tend to smear orientations. a process called precession that slowly rotates orbital axes. A tight cluster suggests a shepherd, or a selection effect, or both. Precession is easy to picture if you think of a spinning top. The orbit's long axis slowly swivels under steady gravitational tugs, and given enough time, those swivels should wash out any original pattern, unless something keeps reining it in. The word suggests matters, because the data are sparse and the sky is biased. Still, the pattern is provocative because the outer solar system is old, and old systems tend to forget their initial conditions. That forgetting is a kind of entropy in orbital space. Without a stabilizing influence, orientations diffuse, and the surviving distribution becomes smooth, so when a small sample looks organized, it feels like a message. The Planet 9 hypothesis is a numerical answer to a geometric pattern. It proposes a body of roughly 5 to 10 Earth masses, often quoted near 10 Earth masses. It places that mass on a distant eccentric orbit with a semi-major axis of hundreds of astronomical units. Astronomical units are the Earth-Sun distance, a unit that keeps the scale human. Neptune orbits around 30 AU. Planet 9 models often place perihelion well beyond Neptune and aphelion far deeper, where sunlight is a rumour. At those distances, even the sun's warmth becomes a background condition rather than a daily reality. Temperatures drop toward just a few tens of Kelvin, and any atmosphere would be tenuous, transient, or locked away as ice. At hundreds of AU, even a large planet would move slowly across the sky, shifting by arc-seconds over weeks rather than degrees over nights. That slow motion is both a clue and a curse. It makes the object easy to confuse with the star, and hard to confirm without careful time baselines. It also changes how you search. You cannot rely on obvious streaks between exposures, so you look for a point that is subtly out of place, then returns with the same slow insistence, an astronomical heartbeat measured in months. A mass like that does not need close encounters to shape the population. Over long times, it can torque orbits through secular effects, slowly rotating their long axes and stabilizing certain configurations. It can also trap objects in resonances that keep them from drifting randomly. Secular effects are the quiet kind of gravity, the cumulative pull that builds over many orbits. They are not dramatic flybys, they are persistent nudges that, over millions of years, can reshape the architecture of a distant population. Another way to say it is simple: gravity is patient. A small acceleration applied for long enough becomes a major change. One key idea is anti-alignment. In several simulations, the extreme TNOs cluster in a direction roughly opposite the perturber's perihelion direction. The smaller bodies avoid the planet's path, yet their orientations remain correlated because the planet's gravity organizes phase space. Anti-alignment sounds paradoxical until you picture it as traffic flow. The objects are not drawn into the planet's lane, they're guided away from it. Yet the guidance still creates order, like a barrier that forces many paths to bend the same way. Phase space is the invisible map of all possible orbital states, and a massive body can carve that map into safe zones and dangerous zones. In the safe zones, orbits circulate without close encounters. In the dangerous zones, trajectories wander until something breaks. Another idea is shepherding into a stable corridor of angles. The perturber can create islands of long-term stability, where objects survive for the age of the solar system. Outside those islands, orbits can become chaotic and eventually get ejected or reshuffled. This is why 6 distant worlds mattered. They looked like survivors of a dynamical filter, not random leftovers. Their orbits looked like they had been sorted. Sorting is a powerful metaphor because it implies a mechanism. If you see a beach where all the stones are the same size, you assume waves did work. If you see orbits that share a direction, you suspect gravity did work. But the ocean in this story is also human. The tension is that sorting can happen in the sky catalogue too, because discovery itself has currents, where we look, when we look, and what we decide is worth chasing. Survey bias starts with where telescopes can look. Ground-based surveys avoid the bright plane of the Milky Way, where star density makes faint moving dots hard to separate. They also avoid regions with high extinction and crowded fields that raise the false positive rate. In a crowded star field, a dim-moving object can be lost in the glare of background sources or mistaken for noise. The problem is not only detection, it is confidence, because a survey must distinguish real motion from artifacts. Season and weather impose another pattern. A survey from a given latitude sees certain right ascensions best at certain times of year. The same patches get revisited because they are convenient, not because nature prefers them. A time-lapse of an observatory dome opening and closing can make this feel physical. The sky rotates, clouds roll in, the moon brightens the background, and the schedule shifts. The catalogue that results is a record of human nights as much as celestial mechanics. Brightness bias is built into detection. Objects are easiest to find near perihelion, when they are closer and brighter. That means discovered objects are not a random sample of all orbits. They are a sample of orbits that bring objects into our detection window. This bias is especially severe for extreme objects because their brightness can change by orders of magnitude across an orbit. A body at aphelion may be effectively invisible even to large telescopes. The same body near perihelion can suddenly become a measurable point. Follow-up bias adds a second layer. Once an object is found, astronomers must recover it to refine the orbit. Recovery is easiest when the object is in a predictable part of the sky and when the field is not crowded. That practical constraint can preferentially keep certain orbital orientations in the catalogue. Orbit determination is itself a process of patience. Early observations span a short arc, and short arcs can mimic many possible ellipses. Only repeated measurements over months and years collapse that uncertainty into a reliable set of elements. There is also a subtle bias in search strategy. Surveys often search near the ecliptic because that is where many solar system bodies are. If extreme objects have higher inclinations, they may be undercounted, and the apparent distribution can be distorted. The Planet 9 debate became, in part, a debate about selection functions. A selection function is a model of what your survey could have found, given its cadence, depth, and sky coverage. Without that model, clustering statistics can be misleading. The phrase sounds abstract, but the meaning is practical. You cannot interpret what you found until you understand what you are capable of finding. In the outer solar system, capability is shaped by limiting magnitude, seeing, cadence, and the algorithms that flag moving points. Those algorithms matter more than most viewers realize. A moving object pipeline has thresholds for significance, rules for linking detections, and filters for rejecting cosmic rays, and each choice can quietly favor one kind of orbit over another. Proponents of the clustering argue that even after accounting for known biases, the angles still look too clustered. They point to the small probability of chance alignment under simple null models. They argue that the pattern persists across independent surveys. Skeptics argue that the null model is not simple, because the discovery process is not simple. They show that certain survey footprints naturally produce apparent clustering, an argument of perihelion and node. They argue that the significance can shrink when you simulate the actual observing history. This is astronomy's version of hearing patterns in noise. The human brain is built to detect structure, even when structure is accidental. In sparse data, the line between signal and mirage is thin. A lingering shot of random static, slowly resolving into a faint pattern, can make the point without words. When the dataset is small, the eye can be too eager, and the mind can be too confident. The documentary's central question sits inside that thin line. Are we seeing a real massive perturber, hinted by orbits, and echoed by infrared candidates? Or are we seeing a statistical artifact that happens to overlap a tempting patch of sky? To keep the mechanics accessible, we need one more translation step. The orbital angles are like a compass bearing for the orbit's long axis. If several bearings cluster, it suggests a preferred direction in the outer solar system. But a preferred direction can come from physics, or from observation. Physics would mean a long-term gravitational torque that keeps the bearings grouped. Observation would mean we mostly looked in the directions where those bearings are easiest to discover. This is where the chapter becomes quietly unsettling, because both explanations can feel plausible. Gravity can organize orbits, and human habits can organize catalogues. The same pattern can be read as a discovery or as a mirage. A thought to linger on is uncomfortable in its simplicity. If you were forced to find a pattern in 6 points, could you avoid finding one? Especially when the stakes make the pattern feel meaningful. If Planet 9 is real, it should leave more than one fingerprint. It should not only cluster perihelion directions, it should also produce a population of high inclination objects, including some on nearly perpendicular or even retrograde paths. That prediction is important because it is harder to fake. A survey footprint might bias longitudes, but it is less likely to manufacture an entire population of objects on steeply tilted orbits. especially if those objects appear in multiple independent datasets. Some models predict a set of objects with inclinations around 40 to 60 degrees and a tail that reaches beyond 90 degrees. Those objects would be hard to find, but they would be a distinctive signature of long-term perturbations. In visuals, the solar system's plane can be a thin sheet of light, while rare orbits arc over it like thrown hoops. A retrograde orbit moving the wrong way can be shown as a counter-flowing track, familiar but deeply strange. Planet 9 models also predict resonant relationships. Several extreme TNOs could occupy mean motion resonances with the perturber, where orbital periods form simple ratios. Resonances can protect objects from close approaches while maintaining alignment. Resonance is not a collision, it is timing. If two bodies return to certain configurations in a repeating rhythm, the gravitational tugs can add coherently, and the orbit can become locked into a stable pattern. A competing interpretation keeps the cause inside the known solar system. Neptune's migration early in history could have scattered objects outward and left them in detached states. In that view, the clustering might be a transient artifact of how the population was emplaced. Neptune migration is not a single event. It is a process where the giant planets exchange angular momentum with a disk of planetesimals. That process can move resonances, capture objects, and sculpt eccentricities and inclinations. Historically, this idea grew from attempts to explain why the Kuiper belt is structured at all, with resonant populations like Pluto's 3-2 resonance. Migration turns the outer solar system into a dynamic place, where the present arrangement is the end of a long rearrangement. Another alternative is many small bodies instead of one big one. A distributed disk of mass in the far outer solar system could exert a collective gravitational effect. It could slowly precess orbits without requiring a single dominant planet. This idea faces constraints, because too much distributed mass would affect known planets and would likely be detectable in other ways, but it remains part of the landscape because it changes the expected fingerprints. A disk produces smoother, less localized effects than a single perturber. A third alternative reaches beyond the solar system. The galactic tide, the Milky Way's gravitational field, can torque very distant orbits over long times. Passing stars can also perturb the outer reservoir, especially early in the Sun's birth cluster. These effects are real, and they are known to shape the Oort cloud. The question is whether they can shape the detached TNO region strongly enough, and in the right way, without a planet. Their fingerprints tend to be broader and more isotropic, though specific stellar encounters can imprint directionality. The historical context matters here, because the idea of unseen perturbers is not new. Neptune itself was predicted from Uranus's orbital deviations, and then found near the predicted position. Yet other predictions, like the hypothetical planet Vulcan, dissolved when better physics explained Mercury's orbit. That history does not decide this case, but it frames the psychology. Astronomy has been rewarded for trusting gravity and embarrassed for overfitting patterns. The same discipline contains both lessons. Each hypothesis predicts a different pattern across multiple orbital elements. Planet 9 tends to create correlated clustering and a high inclination component. Neptune migration tends to create resonant structures tied to Neptune's history, and less persistent angular clustering at extreme distances. A massive distant disk tends to create coherent precession without sharp resonant islands. Galactic tide and passing stars tend to excite perihelia and inclinations in ways that depend on distance and time, often producing wide dispersions. So the 6 worlds are not just 6 dots. They are a test set for competing dynamical stories. Each new extreme object is a new constraint, and each refined orbit can move the statistics. This is why astronomers argue about definitions and thresholds, because small choices change which objects enter the test. A perihelion cut at 30 AU is not the same as a cut at 40 or 50. The extreme category is a lens, and lenses can distort. The sample size problem is unavoidable. With only a handful of objects, any pattern looks dramatic. With dozens, patterns can either sharpen into a clear signal or dissolve into a uniform cloud. This is why the debate has lasted. The outer solar system is hard to survey, and the catalogue grows slowly. Every new discovery arrives with large uncertainties that shrink only after years of tracking. In the meantime, the orbits live as probability clouds. A single object's argument of perihelion can shift as more observations arrive, and a small shift can matter when the sample is small. The chapter's suspense is partly statistical, which is an unusual kind of suspense. There is also a subtlety in what counts as extreme. Some objects have large semi-major axes but perihelia still near Neptune's reach. Others have high perihelia but smaller semi-major axes. The Planet 9 argument typically focuses on those that are both distant and detached. That definition matters because changing the cut changes the statistics. If you include more objects, clustering can weaken. If you include only the most detached, clustering can strengthen, but the sample becomes tiny. The documentary needs to hold both truths at once. The pattern is intriguing enough to motivate a planet-sized hypothesis. The pattern is fragile enough to be destroyed by bias or by a few new orbits. The horror in this chapter is not a jump scare. It is the idea that gravity can hide a major actor in plain sight, and that our inference might still be wrong. If a 10 Earth mass object is out there, it means the solar system's architecture is incomplete. It means formation models must explain how a super-Earth ended up on a distant eccentric path. It means our census failed at the level of a major planet. That failure would be sobering, because the outer solar system is not only empty space, it is where formation theories meet their hardest test, because accretion is slow, collisions are rare, and the sun's influence is weak. If the clustering is a mirage, the horror is methodological. It means we can be seduced by patterns created by our own observing footprint. It means the hunt could be chasing a statistical ghost, while the real explanation is more mundane or more diffuse. And there is a third, quieter possibility. The clustering could be partly real and partly biased, a mixture that makes the pattern look cleaner than it is. In that case, the sky would be telling the truth, but not the whole truth. This tension feeds back into the infrared whisper from Chapter 1. Infrared candidates feel meaningful because orbital math points to regions where a perturber could hide. But that pointing depends on whether the clustering is physical. Here the narrative turns from geometry to prediction. If you accept the clustering as real, you can fit a family of Planet 9 orbits that would maintain it. Those fits produce a broad region of sky where the planet is more likely to be today. The region is broad because the data are sparse and the orbit is long. Different assumptions about mass and eccentricity shift the predicted longitude and latitude. Different choices of which TNOs count shift it again. Even the planet's brightness depends on assumptions, because albedo and size matter. A dark, cold world could be faint invisible light even if it is large, while a brighter surface could make it easier. In infrared, temperature and emissivity become the key variables. At these temperatures, thermal emission peaks in the far infrared, and what matters is not sunlight reflected off ice. What matters is the planet's own stored heat, plus the faint equilibrium glow set by distance from the sun. Still, the prediction is not useless. It narrows the search from the whole sky to a set of swaths, often at moderate ecliptic latitudes. It also suggests the planet would move slowly and would be faint in visible light. That is why infrared surveys matter. A cold object hundreds of AU away emits thermal radiation that can be more detectable than reflected sunlight. Infrared catalogues become a place to look for slow-moving sources that match expected colours. In visuals, the spectrum can slide from visible to infrared, and the cold outer solar system can brighten as if a hidden layer were revealed. The idea is counterintuitive but simple. Cold things glow too, just at longer wavelengths. But infrared surveys have their own biases. Confusion with galaxies and dusty regions can create false candidates. Limited cadence can make motion hard to confirm, especially for objects with tiny apparent shifts. A faint infrared point may be a distant galaxy, a variable star, or an artifact of the detector. Confirming a moving object requires repeated measurements, careful calibration, and a willingness to accept that most candidates will fail. So the breadcrumb trail is real and unreliable at the same time. Orbital clustering points to a region. Infrared catalogues contain sources in that region. The overlap feels like a signal, but it can also be coincidence. The chapter ends with a practical question that sets up the next step. If the outer orbits encode a hidden mass, then the math should tell us where to stare longer. If the math is being fooled by bias, then staring longer might still reveal something else. Either way, the edge of the solar system is not empty. It is a living archive of gravity, written in angles and distances that take centuries to complete. From this point on, the hunt becomes a comparison between predicted sky patches and real photons in infrared catalogues. The next chapter follows that bridge and asks why Akari and similar surveys keep returning to the same dark corridor. Chapter 2 left us with geometry and probability. Chapter 3 follows photons because a hidden mass must also have a temperature. The shift is subtle but decisive. Math can sketch a corridor, yet only light can tell us what occupies it. If something massive is out there, it must exchange energy with its environment, even in the deep freeze. The question is not whether it glows, but whether our instruments can separate that glow from everything else. This is where astronomy becomes less like deduction and more like listening. The sky is loud in its own way, filled with emissions that overlap and interfere. Our job is to isolate a whisper that is physically inevitable, then prove it is not an illusion. Akari enters as a practical tool, not a mythic machine. It was a Japanese infrared space telescope that surveyed the sky in multiple infrared bands. The mission's name means light in Japanese, which feels almost ironic in a chapter about darkness. In practice, Akari was built for a simple promise: map the infrared sky with consistent calibration, then leave behind an archive others could mine. It also belongs to a lineage of infrared astronomy that learned hard lessons. IRIS in the 1980s proved that an all-sky infrared survey could rewrite catalogues overnight. Later missions refined sensitivity and stability, but they also revealed a truth. The deeper you look in infrared, the more the universe fills in. Visually, Akari belongs to a specific era of space astronomy. We see the clean geometry of a cryogenic telescope bus, the reflective gold insulation, and the slow rotation of a survey scan. We see a spacecraft that does not chase targets dramatically, but sweeps methodically, like a lighthouse that never gets tired. That steadiness matters, because the signals we care about are not bright points that announce themselves. In animation, the scan pattern becomes a calm metronome. The spacecraft rolls, the detectors trace long arcs, and the sky is stitched into a mosaic. The pace feels almost indifferent, which is exactly what you want when you are measuring near the noise floor. Infrared matters because cold objects do not advertise themselves in visible light. At hundreds of AU, reflected sunlight collapses faster than the intuition expects. A distant planet can be huge and still look like a fleck of dust, because the lamp that illuminates it is far away. The outer solar system is not merely dim, it is a regime where the usual visual cues fail. One astronomical unit is the Earth-to-Sun distance, about 150 million kilometers. Light crosses that gap in a little over 8 minutes. That travel time is a useful anchor, because it turns distance into delay, and delay into scale. When we say hundreds of AU, we are describing a solar system that stretches into hours of light travel. A simple graphic can make the point land. At 1 AU, sunlight is familiar and sharp, and shadows have edges. By 100 AU, the same sunlight is diluted into a thin wash, and by 300 AU, it is a faint background condition. At 30 AU, Neptune receives about 1/900th of Earth's sunlight. At 300 AU, sunlight is about 1/90,000th. Those ratios are not poetic exaggerations, they are inverse square law arithmetic. The same rule that makes a flashlight fade across a room governs the solar system, only here the room is vast. That dimming is why a distant planet can hide in plain sight. Even a large world becomes a weak reflector when the lamp is far away. The surface could be bright ice, or dark tholin-stained crust, and distance still dominates the outcome. In visible light, you're asking a cold object to act like a mirror in a nearly unlit hall. There is also geometry working against us. At great distances, phase angles are small, so the object is nearly full, yet it is still faint. That sounds helpful until you realize the brightness is capped by how little sunlight arrives in the first place. Infrared astronomy uses a different premise. Objects absorb sunlight and re-emit energy as heat, and heat becomes infrared photons. The emission does not require a shiny surface, only a temperature above absolute zero. That makes infrared feel like a more honest messenger, because it is tied to physics rather than reflectivity. Thermal physics can be said without equations, but it still has structure. If something has a temperature above absolute zero, it glows, and the peak wavelength shifts colder and longer. This is the logic behind blackbody radiation, a concept that once helped launch quantum theory. In plain terms, hotter things glow bluer, colder things glow redder, and very cold things glow in infrared. The blackbody idea is an idealization, and that is useful to admit. Real objects have emissivity, textures, and atmospheres that distort the spectrum. Yet the core message survives. Temperature sets the overall shape, and the shape tells you what kind of thing you might be seeing. Near Earth, warm objects glow in mid-infrared. In the outer solar system, tens of Kelvin pushes emission toward far infrared. That shift is not a minor detail, because detectors and backgrounds change across those bands. A telescope optimized for one infrared window may be nearly blind in another. A Planet 9 class object is expected to be extremely cold. At several hundred AU, equilibrium temperatures can sit around a few tens of Kelvin. That is colder than liquid nitrogen, colder than the coldest Antarctic nights, and closer to the temperature of interstellar clouds. It is a temperature where common materials behave differently, and where sunlight is more memory than warmth. That temperature range is not arbitrary. It comes from balancing faint sunlight absorbed with infrared radiation emitted back to space. The planet intercepts a small trickle of solar energy, then re-radiates it until incoming and outgoing match. The balance depends on distance, albedo, and how efficiently the atmosphere and surface redistribute heat. Even the word equilibrium hides complexity. A slow rotating body can develop temperature gradients, and a thick atmosphere can smooth them out. A high albedo surface reflects more, while a dark surface absorbs more, and both outcomes shift the thermal signature we hope to detect. Internal heat complicates the picture, and it keeps the suspense alive. A massive planet can retain formation heat and radiogenic heat for billions of years. In the giant planets, we see this clearly, because they emit more energy than they receive from the sun. Even a smaller world can store energy in its interior, then leak it slowly through insulating layers. That insulation can be literal. Thick ice shells, high-pressure phases of water, or deep atmospheres can trap heat and release it gradually. The result is a planet that is not merely reflecting the sun, but quietly paying off an ancient thermal debt. If internal heat is significant, the planet is brighter in infrared than sunlight alone predicts. If internal heat is weak, the planet becomes a near-perfect ghost. The difference is not cosmetic, because flux scales with temperature in a steep way. A small change in temperature can translate into a large change in detectability. Akari's advantage is location and stability. Space-based infrared avoids atmospheric absorption that blocks key wavelengths from the ground. Earth's atmosphere is full of water vapor and carbon dioxide, and those molecules carve deep notches in the infrared spectrum. From the surface, you're looking through a veil that changes with weather and altitude. Space also offers a steadier background than Earth's changing sky. That stability matters when signals sit near the survey limit. On Earth, the atmosphere itself glows in infrared, and it flickers with turbulence and temperature gradients. In orbit, the telescope can cool, stabilize, and measure, with fewer moving targets in the foreground. The cooling is not just comfort for the instrument. Infrared detectors see heat, and a warm telescope is a self-inflicted blinding light. So the visuals linger on cryogenic hardware, radiators, shields, and the careful engineering that makes faint photons count. Akari scanned wide areas, building catalogues that look like a thermal atlas. Those catalogues contain stars, galaxies, dust emission, and instrumental leftovers. In a visual sequence, the sky becomes a textured infrared map, where the Milky Way is no longer a band of starlight but a luminous river of dust. The same map that reveals star-forming regions also hides the faint signatures we want. The Planet 9 hunt inside Akari begins as data mining. Researchers search for point sources with the right colours and the right behaviour over time. Colour here means flux ratios between infrared bands, not visible hues. A cold object has a different spectral fingerprint than a warm star, and that difference can be used as a filter. In practice, that fingerprint is a compromise between physics and instrumentation. Bandpasses are wide, calibration has uncertainties, and faint sources wobble in measured flux. So the search is not a single cut, but a sequence of increasingly skeptical tests. The phrase faint infrared signals needs discipline. It can mean a marginal detection that barely clears the threshold in one pass. It can also mean a point source that appears in one epoch and fades in another. It can mean a source that shifts position slightly between observations. Each of those possibilities has a different emotional flavour, but the same statistical danger. Near the threshold, noise spikes can masquerade as real sources, and real sources can be measured poorly. The catalogue becomes a landscape of probabilities, where every dot has an error bar attached to its existence. A real solar system body should move against the fixed sky. That motion is slow at hundreds of AU, but it is not zero. Even when the orbit is leisurely, the geometry of observation forces change. The challenge is that the change can be smaller than the blur of the instrument. Two kinds of motion matter for confirmation. Proper motion is the object's true drift from its own orbit around the Sun. Parallax is the apparent shift caused by Earth's motion around the Sun. Parallax becomes a ruler because nearby objects shift more than distant ones. A useful visual is a split-screen sky. In one panel, a nearby asteroid jumps noticeably between nights, tracing a clear line. In the other panel, a hypothetical object at 300 AU barely nudges, and the shift looks like a rounding error. The audience can feel the difference between obvious motion and ambiguous motion. At extreme distances, parallax shrinks, and that is part of the horror. The object can look pinned to the sky, even while it is moving. The yearly baseline of Earth's orbit is huge by human standards, yet it becomes a small lever against a distant target. This is the same geometry that makes nearby stars wobble more than distant stars. In practice, confirmation demands multi-epoch detections. You need repeated sightings that trace a consistent path, not a single suspicious dot. The path must be consistent with solar system dynamics, not just a random drift. A true object should allow prediction, because gravity is not improvisational. Akari's cadence and resolution set hard limits. If the time baseline is short, motion can be too small to separate from astrometric noise. If the beam is broad, multiple faint sources can blend. Blending can create a fake point that disappears when seen with sharper eyes. Resolution is not a luxury in this regime, it is a form of truth. A broad beam turns the sky into a crowded watercolour, where distinct galaxies smear into one. When you later observe the same patch with a narrower point spread function, the candidate can dissolve into ordinary background structure. The background is not empty in infrared. Distant galaxies glow in infrared, and many are unresolved points at survey resolution. Some galaxies are dusty and red, and they can mimic the colours of a cold solar system object. Confusion becomes a statistical enemy. This is where cosmology intrudes on planetary hunting. Star-forming galaxies contain warm dust that radiates strongly, and active galactic nuclei can produce infrared excess as well. At survey depth, the sky is peppered with extragalactic points, each one a plausible imposter. The universe supplies decoys in abundance. There is a quiet irony here. The same infrared sensitivity that helps find a cold planet also reveals the distant universe behind it. The deeper the catalogue, the more background becomes a crowded population with its own structure and patterns. Galactic cirrus adds another layer of noise. Thin dust clouds in our own galaxy emit infrared light with filamentary structure. Cirrus can raise the background and create ripples that look like sources. Near the detection limit, a ripple can be promoted into a candidate. Cirrus is visually beautiful and scientifically annoying. In infrared maps, it looks like smoke illuminated from within, curling across the frame in pale threads. Those threads are real astrophysical emission, but they are not what we're searching for. They create a textured flaw that makes faint points harder to trust. Instrument artifacts are the third trap. Cosmic ray hits, transient hot pixels, and calibration ghosts can masquerade as faint objects. Artifacts often betray themselves by failing repeatability. A candidate that appears only once is more likely a detector story than a sky story. A cosmic ray strike can be a single bright pixel that the pipeline mistakes for a source. A hot pixel can flare, then cool, leaving a phantom that seems to blink. Calibration ghosts can echo bright objects into nearby positions, like reflections in a lens. The archive is therefore both a treasure and a minefield. So the Akari candidates live in a narrow zone between plausible and fragile. They are not a discovery, but they are not nothing. They are the kind of clue that forces careful language, because certainty is not available yet. In a mystery, this is the moment where the camera lingers on a footprint that might be a shadow. To understand why they matter, we connect back to Chapter 2's math. Orbital dynamics predicts broad regions where an unseen perturber could hide today. Those regions are not a single coordinate. They are swaths shaped by uncertain orbital fits, uncertain mass, and uncertain eccentricity. The uncertainties are not a failure of theory, they are a consequence of sparse data. Many distant objects have been observed for only a small fraction of their long orbits. When you fit an orbit to a short arc, you get a family of solutions, not a single answer. The predicted perturber region inherits that spread. Akari candidates become tantalizing when they fall inside those swaths. The alignment between equations and photons feels like two independent clues converging. One clue comes from gravity, inferred through the motions of other bodies. The other comes from radiation, measured directly as energy arriving at a detector. This is the narrative hinge of the chapter. If dynamics points to a corridor, and infrared catalogues show unusual points inside it, the corridor feels less random. The audience can sense the difference between a blind search and a guided search. Yet guidance is not certainty, especially when the corridor spans a huge area of sky. But the corridor is wide, and the sky is enormous. A wide prediction region increases the chance of coincidental overlap with unrelated infrared sources. In statistics, this is the look elsewhere effect dressed in astronomical clothing. If you search enough pixels, some will always look interesting. That is why the decade-long delay is not automatically suspicious. It can be the expected timescale of a search at the edge of detectability. When the signal is weak, progress is measured in reprocessing, cross-matching, and incremental improvements. The work is slow because the sky does not yield quickly. The object could also be faint for physical reasons. A small radius, a low albedo, and weak internal heat all push brightness down. Each factor is plausible, and they can stack together. A planet that is smaller than expected and darker than expected becomes doubly elusive. Distance dominates everything. If the planet is near aphelion, it is farther, colder, and slower, and every one of those makes detection harder. Farther means less sunlight and less flux at the detector. Colder means the emission peak shifts, possibly away from the most sensitive band. Slower means less motion, which weakens the strongest confirmation test. Slow motion is a special problem. A candidate might move less than a pixel over months, and pipelines are built to reject such ambiguous shifts. The algorithms that protect catalogues from false motion can also erase real motion. In that sense, the search is fighting its own safety features. The object could also be projected against a dense star field. Near the Milky Way plane, confusion rises, and surveys often avoid those regions. Avoidance creates a selection effect that echoes Chapter 2. We search where it is easiest, and we miss what hides where it is hardest. Selection effects are not just academic warnings, they shape the story we tell ourselves. If we avoid crowded fields, we implicitly assume the target is not there. If we prioritize clean regions, we may bias the search towards certain longitudes. The universe does not care about our convenience, but our datasets do. Even when surveys do look, follow-up is expensive. A faint infrared candidate requires time on other telescopes, and most candidates will fail. That failure rate is not discouraging, it is expected, because the background population is large. The discipline is to treat every candidate as guilty until proven real. This is where cross-checking becomes the core method. A credible candidate must be tested against independent surveys with different systematics. Different instruments have different detectors, different scan strategies, and different artifacts. If a source survives multiple independent looks, it becomes harder to dismiss. WISE and NEO-WISE are central references here. They also map the sky in infrared, with repeated passes that can reveal motion. In a visual montage, we see the same sky patch revisited year after year, as if time itself is part of the instrument. Repetition is powerful because it turns a static dot into a moving body. If a candidate appears in Akari but not in WISE, that can mean variability, confusion, or a false detection. It can also mean bandpass differences and depth limits. A cold object may be brighter in one band than another, depending on where its thermal spectrum peaks. Even small differences in sensitivity can decide whether a dot exists. If a candidate appears in both, the case strengthens, but it still is not closed. You still need consistent motion and a plausible orbit. A galaxy will appear in both surveys too, and it will do so with perfect stubbornness. The key is not just detection, but behavior. Ground-based deep imaging adds another test, even though it is not infrared. A large planet might be faint invisible, but deep stacks can still constrain it. Large telescopes can integrate for hours, combining exposures until faint objects emerge. The sky becomes a layered image, where noise averages down and real sources persist. There is a visual patience to this method. Frames accumulate, stars sharpen, and the background grain smooths out. The audience watches time being converted into sensitivity, an abstract trade made visible. Non-detection is also information. If deep optical images show nothing at the candidate position, that constrains albedo and size, or it kills the candidate. A very dark planet could evade optical searches, but there are limits to how dark and how small it can be, while still matching the gravitational story. Each non-detection trims the space of possibilities. The confirmation workflow is repetitive by design. Detect, redetect, measure motion, fit an orbit, predict the next position, recover again. It sounds procedural because it must be procedural. In this regime, excitement without method is a shortcut to error. For a true solar system object, the orbit fit should converge. For a galaxy, the fit collapses because the source does not move. For an artifact, the fit collapses because the source does not repeat. The logic is unforgiving, and that is what makes it reliable. Akari's reported candidates sit in that uncomfortable middle. They are often near survey limits, where significance is marginal and false positives are common. The detections can be real yet poorly measured, which is a particularly frustrating category. It leaves you with a dot that refuses to become a trajectory. That does not make them worthless. It makes them a map of where the boundary between signal and noise is sharpest. In a sense, the candidates outline the frontier of what the survey could plausibly see. They teach us where future instruments must be better, and where follow-up must be most careful. We also need to ground the scale in familiar planets. Jupiter and Saturn are bright in infrared because they are large and have internal heat. Their atmospheres radiate strongly, and their sizes give them enormous emitting area. When we show them in infrared, they look like glowing embers rather than reflected pearls. They also sit much closer, so their apparent brightness is huge compared to any distant super-Earth. Distance and temperature combine into a brutal penalty. A Planet 9 candidate could be several Earth masses, but still much smaller than Jupiter. Smaller radius means less emitting area, and that directly reduces flux. Even if it is warmer than equilibrium, it is still cold in human terms. Tens of Kelvin is closer to deep space than to any everyday warmth. At those temperatures, the world is not just cold, it is chemically quiet, with ices that are rock hard. The environment is so sparse that even sunlight feels like a rumour. So why does infrared still matter? Because at those temperatures, reflected sunlight is close to hopeless, while thermal emission is at least physically guaranteed. The guarantee is weak, but it is real. A planet cannot hide its temperature, only its brightness relative to our instruments. That distinction is important for the audience to hold on to. Visible searches depend heavily on albedo, phase angle, and surface composition. Infrared searches depend more directly on energy balance and internal heat. Neither method is easy, but they fail for different reasons, which is why combining them is so powerful. This is where the documentary's central question returns. If the unseen mass is a planet, it should have a thermal signature even if faint. The signature might be a barely significant point in a catalogue, waiting for a second epoch to confirm it, or it might be buried under cirrus, hidden behind the galaxy's own infrared breath. If the unseen mass is a primordial black hole, the story changes. A black hole has no surface to glow like a planet. It could still produce emission indirectly through accretion, but that emission would be episodic and uncertain. In infrared catalogues, it might leave nothing at all. The contrast is stark, and it is worth lingering on visually. A planet is a body with a surface or atmosphere that radiates continuously. A black hole is an object defined by gravity, not by a glowing skin. If there is no steady thermal emission, then infrared surveys become less decisive, and the search must lean harder on dynamics. That contrast makes Akari's candidates conceptually important. A real infrared point source leans the story toward a planet, though it never proves it. At the same time, a lack of infrared detection does not prove a black hole. It can also mean the planet is colder, smaller, farther, or hidden in confusion. So Akari does not answer the mystery. It sharpens the fork in the road, and it forces the audience to accept how hard the measurement really is. The telescope gives us a new sense, but not omniscience. It shows us that the dark is not empty, and that is both helpful and discouraging. We also need to explain why the candidates persist in conversation. They sit near where the orbital math has repeatedly pointed, across different model variants. The overlap is not perfect, and it should not be presented as perfect. But it is enough to keep attention locked on a particular patchwork of sky. In the mind's eye, that patchwork becomes a stage. We see coordinate grids sliding over star fields, then a highlighted corridor that shifts slightly as models update. We see candidate dots blinking on and off as different filters are applied. The scene communicates a quiet truth. astronomy often advances by narrowing, not by sudden revelation. This is how suspense is built in real astronomy. Independent lines of evidence do not need to be conclusive, they need to be mutually irritating. Each line alone can be dismissed. Together they demand more observing time, more modelling, and more careful bias accounting. Bias accounting is not glamorous, but it is central. Surveys have depth variations, master regions, and detection thresholds that change across the sky. If you do not model those effects, you can mistake a selection artifact for a physical pattern. The outer solar system is especially vulnerable to this, because the sample sizes are small. The decade-long gap since Akari is also a story about infrastructure. Data archives last, but follow-up depends on telescope time and competing priorities. It is also a story about search strategy. A broad predicted region means you can spend years and still cover only a fraction deeply. Akari's archive is therefore both a snapshot and a resource. The snapshot captures the sky at a particular time, with particular sensitivities and limitations. The resource persists, because new algorithms can reprocess old data and extract different candidates. In astronomy, the past can become newly useful when the tools improve. Meanwhile, the outer solar system keeps producing new test particles. Every new detached object is another probe of the gravitational field. Each orbit is like a needle that points, imperfectly, toward the forces shaping it. When you collect enough needles, patterns begin to stand out. Even if infrared candidates are ambiguous, dynamics can sharpen predictions as the sample grows. Objects like 2023 KQ14 matter because they add leverage. Their orbits extend the baseline of what needs to be explained by any unseen perturber. A new orbit can shift the best-fit sky region. It can also reduce the allowed space where a planet could hide without breaking the observed patterns. That reduction is not dramatic in a single step, but it accumulates. The corridor can move, narrow, or split into favoured islands, and each change affects where we look next. So the hunt becomes iterative. Dynamics predicts a region. Infrared catalogues offer candidates. Follow-up kills most. New orbits revise the region. That loop is slow, and it is why the story feels like a whisper rather than a headline. The frontier is measured in years, not days. It is measured in careful reanalysis, in repeated sky passes, and in the patience to accept null results. It is also measured in humility, because the sky at the limit can lie convincingly. The closer you get to the threshold, the more the universe looks like a trick. The chapter ends on a controlled unease. Akari suggests that heat signatures in the dark are possible, and maybe already present. But the same data also show how easily the sky lies at the limit. If Planet 9 is there, it is hiding in the exact place noise looks most convincing. Next, we let gravity tighten the corridor again. We follow the newest distant objects as they refine the map of where the unseen mass can still be. We return to the central question with sharper stakes. Are we watching a cold planet's faint glow, or chasing a shadow cast by something far stranger? Chapter 3 followed infrared photons and found only candidates, because the dark is crowded. Chapter 4 returns to gravity, because a single new orbit can redraw every corridor. In 2023, a new extreme trans-Neptunian object enters the record as a fresh witness. It is designated 2023 KQ14, and it's found near the frontier where the solar system thins. On screen, that frontier is not dramatic in brightness, but in emptiness. Stars hold steady while the solar system's debris drifts almost imperceptibly. The scene can feel almost static, until the motion is pointed out, one faint dot sliding against a background that never flinches. That frontier is not a line, but a regime where periods stretch into millennia. At those distances, sunlight is weak, and even a reflective surface returns only a faint, slow-moving point. The inverse square law is unforgiving here, because doubling distance quarters the light, and the outer solar system keeps doubling. Objects there spend most of their lives beyond easy detection, then briefly swing close enough to be seen. The camera can linger on a time-lapse sky field, where one pixel shifts against a fixed lattice of galaxies. Even the object's motion looks hesitant, an arc measured in nights, not minutes, and confirmed only by patience. The phrase extreme is not poetry, it is bookkeeping with consequences. It generally means a large semi-major axis, and a perihelion far enough out that Neptune cannot casually dominate. In plain terms, these objects live in the deep outskirts, and they only visit the inner edge of that realm. Their visits are short and their evidence is precious. Historically, each new member of this class has forced a recalibration because the sample is small and the dynamical stakes are high. 2023 KQ-14 matters less for its size than for its trajectory through space. A small body can still carry a precise dynamical message because its orbit is the evidence. In celestial mechanics, mass is not required to testify. Motion alone can reveal the sculptor. The object's brightness tells us little about the forces that shaped it, but its path can tell us a great deal. A dim point can still be a loud clue if its geometry refuses to fit the expected background. The orbit is described with the same elements that shaped earlier chapters. Semi-major axis sets the timescale, eccentricity sets the stretch, and inclination sets the tilt. Those are the headline numbers, and they are the ones most viewers learn first. Yet the deeper argument lives in the angles, where geometry becomes history. In the outer solar system, angles are not decorative. They are the memory of repeated tugs, averaged over immense time. The angles still do the real work in this debate. Longitude of ascending node sets the orbit's compass crossing, and perihelion direction sets where the closest approach points. These are not abstract parameters floating in a table. They are the orbit's orientation in three-dimensional space. In a visual overlay, you can draw the ecliptic as a thin glowing plane, then watch the orbit pierce it at the node. The orbit's ellipse can be rendered like a wireframe ring, tilted, rotated, and offset. So the audience sees that direction is literal. When a new object arrives, it is not added like a dot on a map. It is added like a constraint in an equation, and the allowed solutions can shift abruptly. The reason is simple. The outer solar system has few data points, so each one carries disproportionate weight. One orbit can tighten a hypothesis, or it can expose the hypothesis as a fragile coincidence. That is why discovery announcements feel like plot twists, even when the object itself is only a few hundred kilometers across. The immediate twist with 2023 KQ-14s is that its orbit looks suspiciously stable. In a region where chaos is common, stability becomes its own kind of signal. The outer solar system is full of slow instabilities, where tiny gravitational nudges accumulate like interest. If an orbit resists that accumulation, it hints at structure rather than mere survival. The implication is not that the orbit is safe, but that it may be sitting in a protected niche. Stable does not mean perfectly unchanged, and it does not mean untouched by perturbations. Stable means the orbit avoids catastrophic diffusion over immense spans of time. It does not wander into Neptune crossing danger, and it does not get flung outward into the Oort cloud. In practice, stability is measured as bounded behavior in orbital elements, not as rigid permanence. The orbit can breathe, eccentricity and inclination oscillate, yet still remain confined within a long-lived corridor. Scientists test stability with long-term numerical integrations. They take the measured orbit, sample uncertainties, and evolve the system forward and backward for millions of years. The computer does what the human mind cannot. It tracks countless small tugs, step by step, until patterns emerge. The visuals can shift to a dense swarm of simulated trajectories, each one a slightly different clone. Some clones trace tight, repeating loops in element space, while others smear outward, an immediate visual cue for order versus diffusion. They also test for survival across billions of years when possible, because the solar system is old. If an orbit survives that long, it implies a consistent gravitational architecture. The age matters because a configuration that lasts 10 million years may still be temporary. A configuration that lasts 4 billion years begins to look like a designed corridor in phase space. It also implies that whatever sculpted the orbit did not vanish quickly, because the orbit kept its character. These integrations are not one run, and they are not one answer. They are ensembles of simulations, because the orbit we measure is a probability cloud. Every observation has error bars, and every error bar is a different future. In a diagram, the best fit orbit is a bright line, while the uncertainty fan spreads around it like a translucent ribbon. That ribbon can tighten with each follow-up night, as astrometry pins down the object's curvature against the star field. The uncertainty is not just in position, but in velocity, and velocity is destiny. A tiny change in speed at discovery can shift the semi-major axis, and that shifts the resonance landscape. The further out you go, the more a small uncertainty can translate into a large difference in period. This is why follow-up observations weeks and months later can change the story. A longer observational arc turns a tentative ellipse into a measured one. Less guesswork, more geometry. In many cases, the question is whether the object is protected by resonance. Resonance protection is timing that prevents close encounters from accumulating into chaos. It is not a shield in the physical sense, but a rhythm in the gravitational conversation. The object and Neptune, or the object and a hypothetical planet, keep meeting at safe phases. The protection can be subtle, because the object never needs to come near the perturber for the timing to matter. A mean motion resonance is a ratio of orbital periods that repeats a geometry. If the ratio is stable, gravitational kicks arrive in a pattern that can cancel rather than compound. The classic examples are in the asteroid belt, where Jupiter's resonances carve gaps, and in the Kuiper belt, where Pluto survives in a 3.2 resonance. That historical context matters because it shows resonance is not a speculative trick, but a proven organizing principle. Resonances were recognized early in celestial mechanics because they leave fingerprints, gaps, clumps, and survivors across many parts of the solar system. Resonances can act like guardrails in phase space. They do not remove perturbations, but they keep the orbit from wandering into the worst regions. In a visual metaphor, the orbit is a marble rolling on a contoured surface, and resonant islands are basins that keep it from drifting. The marble still moves, but it stays in the basin unless a strong shove arrives. Near the basin's rim, the motion can become erratic, an edge where stability frays into chaos. For distant objects, resonance can also preserve a perihelion distance that stays detached from Neptune. That detachment is the key to whether Neptune alone can explain the orbit. If perihelion stays far enough out, Neptune cannot deliver repeated close encounters, and its influence becomes mostly secular and indirect. The object becomes harder to explain using only the known planets. In that sense, detachment is a diagnostic, because it separates scattered by Neptune from shaped beyond Neptune. So 2023 KQ-14 becomes a test of competing stories. If Neptune can produce and maintain such stability, the Planet 9 case weakens. If Neptune cannot, then something else must be shaping the long-term structure. That something could be a massive planet, or it could be a different kind of perturber. The orbit is not just a location, but a verdict on which mechanisms can plausibly operate at this distance. The phrase, suspiciously stable, is not a headline claim. It is a dynamical diagnosis. It means the orbit sits in a region that looks organized rather than random. In chaotic regions, nearby initial conditions diverge rapidly, and clones scatter across many outcomes. In organized regions, clones stay clustered, as if the phase space itself is guiding them. That guidance can be quantified with measures like Lyapunov times, but the intuition is simple. Chaos forgets, while structure remembers. Organization is the theme of this entire hunt. The earlier clustering claims were about angles that should have been smeared by time. Over hundreds of millions of years, precession should rotate perihelion directions like hands on a clock. If the hands are not uniformly distributed, something may be synchronizing them. The synchronizer does not need to be dramatic. It only needs to be persistent, because persistence beats strength when the clock runs for billions of years. A stable orbit adds a second kind of organization. It suggests the object is not merely surviving, but surviving in a way that requires a persistent pattern of forces. Persistence is the key word, because a one-time event leaves a different signature than an ongoing shepherd. The orbit becomes a long exposure photograph of gravity at work. The longer the exposure, the more the blur reveals a pattern, and the less it looks like a random walk. This is where one object can force a model to change. Models are tuned to reproduce the distribution of known orbits, and each new orbit changes the fit. The outer solar system is not like a lab experiment with repeated trials. It is a single system with limited samples. That scarcity makes every new witness unusually powerful. It also makes humility necessary because a pattern can harden into truth too quickly when the sample is thin. Fitting is not cosmetic and it is not optional. A proposed Planet 9 orbit must reproduce multiple features at once, or it becomes a story without mechanics. It must explain why some objects are detached, why some are tilted, and why certain angles appear to cluster. If it explains only one feature, it risks being an overfit to noise. The best fits are the ones that survive new witnesses without needing constant reinvention. The fit includes the clustering or anti-alignment pattern discussed earlier. It also includes the existence of detached perihelia and a spread of inclinations. Those features are not independent because the same perturbations that rotate perihelia can also pump inclinations. A good model must produce the correlations, not just the marginal distributions. In other words, it must explain why certain combinations of elements appear together, why the solar system's edge seems to prefer some geometries over others. When 2023 KQ14 is added, the statistics can tighten or unravel. A new data point can strengthen clustering, or it can dilute it into noise. The viewer can imagine a scatter plot of perihelion directions, where each point is a faint star, and one new point changes the apparent pattern. In small number statistics, the eye is easily fooled, and the math must be cautious. Even the definition of the sample, where extreme begins and ends, can change the outcome. If the new orbit aligns with the existing pattern, it reduces the chance of coincidence. If it points elsewhere, it raises the chance that earlier alignment was selection. The difference can hinge on a few degrees, which is why the observational arc matters. A short observational arc produces a fuzzy orbit, and a fuzzy orbit produces ambiguous alignment. The narration can slow here, because the suspense is not in discovery, but in refinement, night after night of follow-up that turns uncertainty into a sharper angle. The key is that 2023 KQ14 is not just another extreme object. It sits at a distance where the dynamical environment is especially sensitive to weak, long-term torques. In the inner solar system, strong forces dominate and timescales are short. Out here, the forces are gentle, but they have billions of years to act. A near-constant torque that would be irrelevant over a human lifetime can rewrite an orbit over geological time. Weak torques are the signature of a distant perturber. They do not fling objects in a single encounter, but they can rotate and shepherd orbits over deep time. A torque changes angular momentum direction, which changes the orbit's orientation. In plain language, it is the difference between a punch and a steady hand on a spinning top. The steady hand wins, not by force, but by duration, an influence applied through countless revolutions. In Planet 9 models, those torques often produce anti-alignment. The small body's perihelia cluster roughly opposite the perturber's perihelion direction. This configuration can be stable because it minimizes close approaches, even when the orbits are elongated. It is a kind of gravitational detente, maintained by geometry. The bodies can share space without sharing danger, because their closest points occur on opposite sides of the Sun. Anti-alignment is a stable configuration in many simulations. It keeps the small bodies away from the planet's path while still locking their orientations. The locking is not absolute, but it is statistically persistent. Like a compass needle that wobbles yet points north. The wobble matters, because it sets the width of the allowed island. If the wobble is too wide, the island dissolves into circulation, and the pattern becomes indistinguishable from chance. Adding 2023 KQ14 can therefore constrain the perturber's perihelion direction. If the object participates in the same anti-aligned island, the planet's direction becomes less flexible. In a corridor map of the sky, the allowed region narrows and the search becomes more targeted. If it does not participate, the corridor can fracture into competing possibilities. That fracture would not end the hunt, but it would change its logic. Less one organizer, more many pathways. It can also constrain the planet's inclination. The planet's tilt affects how it pumps inclinations in the distant population and how it sculpts the three-dimensional distribution. Inclination is not just a number, it is a record of vertical stirring. A highly inclined perturber can lift orbits out of the ecliptic, creating a halo-like population. Visually, the solar system's familiar flatness becomes an illusion, as distant rings tilt and cross like interlaced hoops. The longitude of ascending node of the planet becomes a lever too. Change the node, and the plane of influence rotates, shifting which orbits can remain stable. This is easier to see visually than verbally. Rotate a tilted ring in space, and watch which distant orbits it intersects. The node determines where the tilt is anchored relative to the stars. It is the hinge point where the orbit's plane cuts the ecliptic, and hinges matter when you're building a three-dimensional architecture. These parameters are not independent in practice. Mass, semi-major axis, eccentricity, inclination, node, and perihelion direction trade off against each other in the fits. A more massive planet can sit farther away and still torque the population. A less massive planet may need a different eccentricity to achieve the same shaping. This is why the same dataset can yield different best planets, depending on priors and on how uncertainties are handled. That trade-off is why the predicted sky corridor keeps moving between papers. Each team chooses a slightly different dataset, a slightly different cut, and a slightly different prior. Some teams emphasize only the most extreme objects, while others include a broader population to reduce bias. Each choice changes the inferred architecture, sometimes subtly, sometimes dramatically. The corridor is not a single arrow, but a probability band, wide, shifting, and sensitive to new witnesses. 2023 KQ14 forces those choices into the open. If you include it, your model must explain it, and your uncertainty budget must absorb it. If you exclude it, you must justify why it is not part of the relevant population. The argument becomes not only about gravity, but about classification and methodology. Even the language of detached and scattered becomes a battleground, because labels decide which objects count as evidence. This is the scientific process in its most honest form. Competing teams run simulations, compare outcomes, and argue about which assumptions are justified. The debate is not a sign of failure, it is the mechanism by which weak signals are tested. In the background, conferences and preprints become the arena where these assumptions are challenged. The audience can be shown the human side, plots on screens, scribbled notes, and the slow convergence that comes from disagreement. They also argue about what counts as stable. Stability can mean surviving without ejection, or it can mean preserving specific angles without diffusion. The distinction is crucial because an orbit can remain bound yet lose all memory of its initial orientation. For Planet 9, memory, especially angular memory, is often the core claim. The question is not just whether objects exist, but whether they remain organized in the way the hypothesis requires. A model can keep an object bound while still scrambling its orientation. For the Planet 9 debate, orientation is often the more important survival criterion. If perihelion directions randomize, the clustering dissolves even if the objects remain. So, stability is not merely about existence, but about coherence. Coherence is the difference between a population that is merely present and a population that is being actively guided. Small changes in assumptions can flip the result. A different Neptune migration history can change which resonant pathways exist and which detached orbits are reachable. Migration is not a minor footnote, because the giant planets did not form where they are now. In the early solar system, shifting resonances could capture and release bodies, leaving survivors in unexpected places. The Nice model era made this idea mainstream, and it reframed the Kuiper belt as a record of planetary movement rather than static formation. Initial conditions matter too. If you seed the early disk differently, you can produce different survivors, and those survivors can mimic or erase clustering. A disk with a sharp outer edge behaves differently than a disk with a long tail. A disk with more mass changes the self-gravity and the damping, even if only slightly. Those details sound technical, yet they decide which orbits are even reachable, and which are dynamically forbidden. Even the integration method matters at the margins. Step size, treatment of close encounters, and how you model the giant planets can change long-term diffusion rates. Over billions of years, tiny numerical biases can accumulate, so teams cross-check with different integrators. The viewer can be shown a split screen of two simulations that begin identical, then diverge slowly. That divergence is not a mistake, it is a reminder. Chaotic systems amplify the smallest differences, including numerical ones. None of this is a weakness of science, it is the cost of mapping a chaotic system. The outer solar system is a dynamical laboratory with incomplete initial data. We cannot rewind the solar system to its beginning and watch it evolve. We can only infer the past from the survivors, and survivors are a biased sample. The bias is physical as well as observational. Only certain orbits avoid destruction, so the catalogue is already filtered by survival. So the map is not fixed, and it never was. Each new object is a new survey marker, and each marker can bend the best-fit coastline. The coastline metaphor is apt because the boundary is irregular and scale-dependent. Zoom in, and you see new bays and peninsulas. Zoom out, and the outline smooths. The narrator can let the audience feel that uncertainty as a landscape, not a flaw, an edge still being charted. In this chapter, 2023 KQ14 is the marker that bends the coastline sharply. It forces the question of whether the architecture is being actively maintained. Actively here does not mean fast, it means persistent across time. The forces are quiet, but they may be continuous. If the orbit's stability is real, then something has been keeping it real for most of solar system history. Resonances and shepherding are the mechanisms that make maintenance plausible. A massive unseen planet can trap objects in mean motion resonances and keep them detached. The trapping can occur when the object's period becomes commensurate with the planet's period. Once trapped, the orbit can librate around a stable angle rather than circulate freely. Libration is a technical word, but the picture is simple. An orbit rocking back and forth around a preferred geometry, as if tethered. Trapping is not permanent for every object, but it can be long-lived. In phase space, resonant islands can hold bodies for the age of the solar system. The island has boundaries, and near those boundaries chaos can leak in. That detail matters because stable can mean stable for some clones, rather than for all. When the clone swarm is shown on screen, stability looks like a tight braid, while instability looks like fraying threads. Shepherding also sculpts inclinations. A distant perturber can lift orbits out of the ecliptic, creating a population that looks dynamically heated and oddly tilted. The heating is a measure of orbital excitation, not temperature, and it reflects energy stored in eccentricity and inclination. In visuals, the ecliptic becomes a thin sheet, while the distant objects form a puffed, warped cloud. The cloud can be lit like dust in a projector beam, thin yet unmistakably three-dimensional. This is one of the signatures that is harder to fake with observational bias alone. Bias can hide high-inclination objects, but it cannot easily manufacture their dynamical pathways. If a model requires a pathway that does not exist under known physics, the bias argument cannot rescue it. The pathway must be dynamically plausible, not just statistically convenient. That is why dynamical arguments carry a different weight than purely statistical ones, even when both are uncertain. A planet can also create detached orbits by raising perihelia. It can do this through secular interactions that slowly exchange angular momentum without close encounters. Secular effects are averaged over many orbits, like a long-term tide rather than a single wave. They can rotate the line of apsides and shift perihelion distance gradually. The mathematics is a kind of smoothing, where the fast orbital motion is averaged away, leaving a slow drift in orientation and shape. The result is a body that never comes near Neptune, yet still carries Neptune's indirect history. It becomes a fossil that was moved without being touched. That fossil metaphor is useful because it emphasizes preservation. The orbit can preserve a record of forces long after the event that created it. The question becomes whether 2023 KQ-14 is a fossil of early rearrangement, or a fossil still being curated by an unseen hand. If 2023 KQ-14 is detached and stable, it strengthens the need for a consistent perturber. If it is detached but explainable by migration, it weakens that need. The distinction depends on whether Neptune's past can plausibly place it there and keep it there. The keep it there part is often the harder requirement. Creating an orbit is one problem, but maintaining it against diffusion for billions of years is another. So the debate sharpens into competing explanations that must now account for one more witness. The witness is not neutral, because its stability is itself a clue. A chaotic orbit would be less informative, because chaos can produce many outcomes. A stable orbit narrows the range of histories that can lead to it. Narrowing is what makes the discovery consequential, because it reduces the number of stories that can survive. One alternative is that 2023 KQ-14 is a fluke. In a sparse sample, rare configurations can appear meaningful even when they are random survivors. The human mind is tuned to find patterns, especially in small data sets. The scientific defense against that tendency is simulation and careful accounting of selection effects. A thought-provoking question hangs in the air. How many coincidences does it take before coincidence becomes an unlikely explanation? Another alternative is observational selection. The object was found where surveys look more often, and its orbit may be part of a discovery footprint rather than a physical cluster. Many surveys avoid the crowded Milky Way plane, where background stars complicate detection. That avoidance can create angular gaps that look like dynamical structure. The sky itself becomes an instrument artifact, an unevenly sampled sphere that can masquerade as physics. Selection is not only where telescopes point, but when they revisit. Follow-up cadence can preferentially keep certain orbits in the catalogue, while others are lost. If an object moves into a dense star field, it can become hard to recover, and its orbit remains uncertain. The catalogue is therefore shaped by persistence as much as by discovery. In that sense, the known population is partly a record of what was easy to keep, not only what was easy to find. To test this, teams build synthetic populations and run survey simulators. They ask whether the same discovery process would produce the same angular patterns. The simulator includes limiting magnitudes, sky coverage, weather losses, and cadence. It is an attempt to model the telescope as part of the experiment, not as a neutral observer. The visuals can show a simulated sky being scanned in strips, bright where coverage is dense, dim where it is absent, so bias becomes something you can see. If the simulated surveys reproduce clustering without a planet, the Planet 9 claim weakens. If they cannot, the planet remains the simplest organizer. Yet simplest must be weighed against prior probability and against other constraints. A simple explanation can still be wrong if it conflicts with independent evidence. The audience is invited to sit with that discomfort, because the cleanest story is not always the true one. But simplicity is not the same as truth. A planet is a clean explanation, yet the outer solar system can also be shaped by early stellar encounters. The Sun likely formed in a cluster, and close passes were more probable in that crowded nursery. A passing star could torque the outer disk, lifting perihelia and tilting orbits in a single episode. That possibility has been discussed for decades, especially as we learned how common clustered star formation is in the galaxy. A passing star in the Sun's birth cluster could lift perihelia and tilt orbits. That mechanism can create detached objects without requiring a present-day perturber. The historical context matters because it reminds us the solar system's early environment was not isolated. The question is whether that early disturbance can also produce the specific coherence we think we see today. If the disturbance was brief, why would the angles remain organized after billions of years of precession? The question is whether such a scenario also produces long-term stability islands that match what we see. A one-time encounter leaves a different fingerprint than ongoing shepherding. An encounter can create a broad distribution of orientations, then let them precess freely. A shepherd can maintain alignment, resisting that free precession. The difference is not merely theoretical. It determines what patterns should persist as the sample grows. A distributed mass disk is another alternative. A distant disk can cause coherent precession, but it tends to be smoother and less resonant than a single planet. A disk produces a more axisymmetric potential, and axisymmetry tends to smear sharp angular features. That does not rule it out, but it changes what signatures we should expect. If the outer solar system is being guided by a disk-like mass, the organization might look like a gentle drift, not a set of discrete islands. If 2023 KQ-14 sits in a sharp resonant structure, a disk explanation struggles. If it sits in a broad precession pattern, a disk becomes more plausible. The difference is subtle, and it often emerges only after long integrations. This is why teams focus on whether the orbit librates around a resonant angle or circulates freely. Libration is the telltale of a trap, while circulation is the signature of a freer, more averaged influence. So what signatures would decisively favour a massive perturber? The strongest are resonant chains, persistent anti-alignment across many objects, and a high inclination population. A chain is especially compelling because it is hard to generate by chance. Multiple objects in related resonances suggest a common sculptor, not independent accidents. The question becomes almost forensic. Do we see a set of orbits that look engineered by the same hand, or a set that merely survived the same hazards? Another signature is a specific relationship between semi-major axis and perihelion distance. Planet 9 models often predict detached objects in particular ranges and gaps. Those ranges arise because resonances and secular effects are not uniform across distance. Some regions are stable harbours, while others are turbulent channels. A visual can show these regions like coloured bands, green for long-lived stability, red for rapid diffusion. So the audience sees that distance alone does not determine fate. Gaps matter because they imply dynamical clearing. A planet can carve forbidden regions in phase space, leaving a structured distribution rather than a smooth continuum. This is the same logic that makes Kirkwood gaps meaningful in the asteroid belt. Absence can be evidence when physics predicts where absence should occur. In the outer solar system, the gaps would be harder to see, but they would be more consequential because the forces are weaker and the timescales longer. If 2023 KQ-14 falls into a predicted island, it strengthens the case. If it sits in a region the planet should have cleared, it becomes a problem. Problems are valuable because they force refinement or rejection. A hypothesis that cannot be falsified is not a map, it is a mood. The narration can linger on that idea because it is the difference between science and storytelling. This is why the discovery is a twist rather than a simple addition. It can either tighten Planet 9's allowed orbit, or it can challenge the hypothesis entirely. Tightening means the model must thread more needles at once. Challenging means the model begins to demand parameters that conflict with other lines of evidence. Either way, the orbit changes the geometry of belief. What was plausible yesterday becomes less plausible today. Tightening means narrowing the planet's possible inclination and node. It also means narrowing the perihelion direction that keeps the population stable and anti-aligned. In a visual, the sky corridor shrinks from a broad band to a thinner arc. The narrator can let the audience feel the pressure of constraint, as if walls are closing in. Each new orbit is another wall panel sliding into place, reducing the room where the planet can hide. Challenging means forcing the planet's parameters into uncomfortable extremes. A planet that must be too massive, too inclined, or too distant begins to conflict with other constraints. A very massive planet should leave stronger secular signatures on known planets. A closer planet should have been seen more easily in deep surveys. The model begins to look less like a natural solution and more like a strained compromise. Those constraints include the absence of a direct detection so far. Infrared candidates exist, but no confirmed moving object has closed the case. The absence is not trivial because modern surveys are powerful and persistent, yet the sky is vast and faint slow movers can hide in plain sight. If the motion is slow enough, even a real planet can masquerade as a fixed point unless the survey cadence is designed to catch it. A planet that is too warm should have been seen in infrared surveys. A planet that is too close should have been seen in deep optical searches. A planet that is too massive should leave stronger signatures in known planetary motions. The allowed space is therefore a narrowing corridor, bounded by multiple kinds of silence. Silence is not proof of absence, but it is a constraint, an empty region on the map that must be explained. 2023, KQ-14 pushes on that corridor from the dynamical side. It says the architecture at the edge is either finely tuned or our interpretation is incomplete. Fine-tuning can be real, but it demands explanation. In nature, delicate structures usually persist because something maintains them. The question becomes almost philosophical. Is the outer solar system a museum of ancient accidents, or an ecosystem still being shaped? This is where the tone becomes courtroom rather than treasure hunt. The solar system's edge becomes a place where gravity is the judge and orbits are testimony. The courtroom is cold and quiet, and the testimony is slow. The evidence arrives not as a confession, but as a curve traced across decades of observation. Each astrometric point is like a word in a statement, and the statement only becomes legible when enough words accumulate. Each orbit is a sworn statement written in angles and periods. The statement is long, slow, and hard to read, but it is not easily forged. A forged story would require coordinated bias across many surveys and many years. A genuine dynamical pattern, by contrast, persists, even as instruments and teams change. The longer the record, the harder it becomes to dismiss the pattern as a quirk of one telescope's habits. Every new object either strengthens the prosecution or strengthens the defense. It either supports a hidden perturber, or it exposes our bias and overfitting. Overfitting is the danger of building a model that explains the known sample too well. In a small dataset, a model can become a mirror of the noise. The viewer can be asked to consider a simple question. Are we seeing a law of nature, or a story we built from too few points? The fear is not that we will never find the answer. The fear is that the answer may not be a planet at all, even if the gravity is real. That is a subtle fear, because it separates the inference of mass from the identity of the mass. The outer solar system could be organized by something that does not shine. In that possibility, the darkness is not just the absence of light, it is the presence of something indifferent to light. Because gravity does not care what carries mass. A 10 Earth mass influence could be a cold planet, or it could be something that emits almost nothing. The equations respond to mass and distance, not to reflectivity or temperature. That indifference is what makes the hunt both powerful and unsettling. It means the solar system can be shaped by an object that refuses to announce itself in any wavelength we routinely monitor. If a planet is not the only way to get the gravity we infer, what else could mimic it? The next chapter enters the most unsettling possibility, a tiny black hole older than the Sun. We leave 2023 KQ-14 as a final unresolved witness. Its stability redraws the map, and it tightens the question we cannot avoid. Are the infrared whispers and the organized orbits pointing to Planet 9? Or are they pointing to a darker kind of mass, hiding where even heat is silent? Chapter 4 tightened the dynamical corridor and made the silence feel intentional. It narrowed the range of orbits where a hidden mass could live, and it made every empty pixel feel like a decision. Chapter 5 asks a harder question, because it changes what hidden even means. What if the mass is real, but it is not a planet? A planet is a familiar compromise between gravity and light, a body that both tugs and glows in ways we can predict. It reflects sunlight with a brightness set by size, distance, and albedo. Plain language for how shiny its surface is. That reflected light is not magic, it is geometry and scattering, with phase angle and surface texture quietly shaping the signal. A planet also radiates heat, because anything above absolute zero emits thermal photons, even if the warmth is barely more than the cosmic background, and it occupies a volume you can imagine, a sphere with a radius that sets its silhouette, its cross-section, and the scale of any atmosphere. A black hole is gravity without a surface, and that changes what our telescopes should expect. It is not merely a dark rock or an icy world with a dim atmosphere, waiting for a bigger mirror to reveal it. It is a region where space-time is curved so steeply that light cannot climb out, no matter how long it tries. If a planet is a thing you can paint, a black hole is a boundary you can only infer, an edge defined by escape speed rather than by matter. The hypothesis begins with primordial black holes, or PBHs. These are hypothetical black holes formed from density fluctuations in the early universe, long before stars existed and long before heavy elements were forged. They are not made by dying stars, and they do not require a supernova, a neutron star, or any ordinary stellar life cycle. They would be relics from the earliest cosmic conditions, like fossils that never needed biology, preserved because gravity can lock history into a single compact object. In the first moments after the Big Bang, the universe was hot and expanding fast, and it was also noisy with quantum fluctuations. Inflation, if it occurred, would have stretched tiny variations into macroscopic seeds, turning microscopic randomness into cosmic structure. Most of those seeds became the gentle ripples that later grew into galaxies, the same ripples we still read in the cosmic microwave background. But in some models, rare peaks could have been high enough that gravity briefly won, collapsing matter faster than pressure and expansion could dilute it. Tiny overdensities could have collapsed if they were heavy enough and compact enough, and if pressure and expansion could not tear them apart. The key is timing, because the early universe had a horizon. Only regions smaller than a certain size could communicate and equilibrate. A collapsing patch had to fit inside that causal boundary, while still containing enough mass to overwhelm radiation pressure. If that happened, the result would be a black hole relic, older than galaxies and older than the Sun, carrying information about primordial conditions we can otherwise only model. PBHs are not a single prediction with one mass scale, and that is part of their allure. In theory, they could span a wide range, from asteroid mass to far larger, depending on when they formed and on the spectrum of early fluctuations. Earlier formation tends to mean smaller mass, because the horizon mass was smaller then, and the universe had less time to gather energy into one region. Later formation allows larger masses, because the universe had expanded and the horizon encompassed more material. Most of those ranges are constrained, but not all are eliminated, and the surviving windows keep the idea alive. The phrase grapefruit-sized black hole sounds like a trick, but it is a geometry fact. Black hole size is set by the Schwarzschild radius, which comes straight from general relativity's simplest solution for a non-rotating mass. That radius scales linearly with mass, not with density, composition, or any familiar material strength. Double the mass, and the radius doubles, even though the object is not made of anything in the normal sense. For an Earth-mass black hole, the Schwarzschild radius is only centimeters, roughly the scale of a coin. It would be smaller than a grapefruit, yet it would weigh as much as Earth, and that mismatches the point. The contrast is so extreme that the mind resists it, because we associate mass with bulk and volume with presence. But gravity does not care about our intuition, and the equations are unembarrassed. Mass curves space-time, whether it is spread out like a planet or compressed beyond any material limit. Its gravity at distance would match any other Earth mass object, because far away it behaves like a point mass. In Newtonian terms, the force depends on mass and separation, not on whether the mass is spread out or compact. In relativistic terms, the external spacetime of a non-rotating mass is the same outside its radius, described by the same metric. The outer solar system mostly measures that external field, because our tracers are far from the putative object and sensitive to long-term averaged tugs. This is the first key point for the Planet 9 debate. The outer solar system evidence is gravitational, not photographic, and it arrives as a pattern rather than a portrait. The TNO clustering arguments and long-term talks respond to mass and orbit, not to what the mass is made of, and not to what it looks like. When we fit the data, we are fitting a gravitational influence, not a surface, and that distinction becomes uncomfortable once you admit objects that do not shine. If the inferred perturber is 5 to 10 Earth masses, gravity does not demand a cold planet. A PBH with the same mass on the same orbit would shepherd TNOs in the same way, nudging perihelia and shaping long-term stability islands. The equations would not notice the difference because the dominant term is the monopole gravitational pull, and that term is blind. The unsettling implication is that our best evidence might be composition blind, and that planet is a story we tell to make the mass feel familiar. That indifference is the unsettling part of the hypothesis, because it turns a searchlight into a scale. We have been treating darkness as a problem of faint light, as though the object is merely too far and too cold, waiting for better detectors. A PBH turns darkness into a property of the object itself, dark not because it is dim, but because it has no surface to shine. The absence becomes intrinsic, and the silence stops feeling accidental. A cold planet should still do certain things, even if it is distant and slow-moving. It should reflect some sunlight, even if weakly at hundreds of AU, because ice and haze scatter photons, and because geometry never fully turns off. It should also emit thermal radiation, set by equilibrium temperature, plus any internal heat from contraction, radioactivity, or residual formation energy. Even a planet with little sunlight still has a thermal budget, and that budget sets expectations for where to look. At 400, 600, or 800 AU, sunlight is diluted by distance, and equilibrium temperatures fall to tens of Kelvin. That is cold enough that the peak emission shifts into the far infrared and submillimeter, where detectors fight background noise and where the sky itself glows. Yet the spectrum should still resemble a black body-like curve, modified by atmospheric opacity and surface properties, and shaped by emissivity. In other words, it should have a predictable colour in heat, even if the signal is faint. A PBH does not reflect sunlight because it has no surface. It also has no steady planetary thermal glow, because there is no atmosphere or crust radiating at tens of Kelvin, and no area to radiate from in the usual sense. The event horizon is not a material shell, and it does not behave like a cold rock, even if the mass is the same. In most cases it would be electromagnetically quiet, not because it is hidden behind dust, but because there is nothing to radiate. There is a subtle caveat here, and it matters for honesty. Black holes do have Hawking radiation in theory, a quantum effect that makes them emit extremely faint thermal particles as if they had a temperature. But for Earth mass black holes, that emission is fantastically small, far below any conceivable detection, and far below astrophysical backgrounds. So for practical astronomy, the PBH is dark, and it stays dark for longer than the age of the universe. That does not mean a PBH is perfectly invisible, because invisibility is an environmental statement. It can interact with matter around it, and that interaction can create signatures, but only when the environment provides fuel. The key is that the signatures are not steady and not guaranteed, and they may be rare enough to miss for decades. A planet is a lamp with a dimmer. A PBH is a trap that only lights up when something falls in. If a PBH captures dust, gas, or small bodies, infalling material can heat up as gravitational potential energy converts into kinetic energy. Near the black hole, that energy can become radiation through shocks, compression, and magnetic turbulence, especially if the inflow forms a disk. Accretion can produce X-rays and other high-energy emission, depending on the rate and the geometry of the inflow, and on how efficiently the gas radiates. At the low densities of the outer solar system, the rate is expected to be tiny, which keeps the scenario plausible and frustrating. The outer solar system is not empty, but it is thin, and that thinness is crucial. The solar wind is weak out there, and interplanetary dust density drops with distance, leaving long volumes of near vacuum between grains. Gas is scarce, and the Kuiper belt is a sparse archipelago rather than a fog, with objects separated by enormous gaps. A PBH could orbit for millions of years and rarely encounter anything that feeds it, which means the default is quiet. Even a tiny accretion rate could create occasional flares, but the probability is uncertain. A small comet or rubble pile could wander too close, become tidally disrupted, and briefly generate a hot stream that spirals inward. The flare would be brief on astronomical timescales, and it might be localized to X-rays or radio, depending on density and magnetic fields. Yet most of the time there may be nothing to feed on, and the PBH would remain silent, present without announcing itself. This is why the infrared whisper becomes ambiguous in a new way. A planet explanation expects some thermal emission, even if faint and model dependent, because a planet has a radius and a temperature, and those are measurable. A PBH explanation can tolerate an infrared non-detection without strain, because darkness is the default state, not a puzzle. The same absence that frustrates one model can comfort the other, and the silence becomes evidence only through comparison. So the observational questions shift from brightness to behaviour. What evidence would separate a PBH from a cold planet, if gravity alone cannot, and if both can sit in the same dynamical corridor? What would we look for when the object refuses to be an object in the usual optical sense, and when our usual instincts fail? The answer is not a single signature, but a set of discriminators that point in one direction when combined. The first discriminator is reflected sunlight. If repeated deep optical imaging finds a moving point source with a plausible orbit, that strongly favours a planet because it implies a scattering surface with a finite radius. The motion matters because it ties the light to the dynamical hypothesis rather than to a background star, galaxy, or detector artifact. A PBH would not produce that moving reflected light signature, except through indirect effects like a transient dust cloud, which would have its own problems. The second discriminator is thermal emission. A planet should have a spectrum consistent with a cold blackbody-like emitter, modified by atmosphere and albedo, and it should be stable over time. A PBH should not show a stable far-infrared thermal peak tied to a physical radius, because there is no radiating surface to set one. If we can measure a radius from thermal flux and temperature, the PBH idea collapses, and the object becomes a world again. The third discriminator is accretion emission. A planet can have aurorae, lightning, and magnetospheric radio, but it will not produce an accretion disk that heats to extreme temperatures. A PBH could, in rare circumstances, produce X-ray or radio signatures from infalling material, especially if a disrupted body forms a temporary disk. The keyword is rare because the outer solar system offers little fuel, and rarity makes detection a matter of patience. There is also a difference in variability, which telescopes can exploit. Planetary emission is steady on human timescales, with slow seasonal or rotational modulation that repeats and can be modelled. Accretion emission is episodic, with sudden rises and decays shaped by the orbital dynamics of debris and by how quickly the disk drains. If we ever saw a faint source that flared and then vanished, and if it also moved with the slow drift of a distant solar orbiting object, the story would change. The fourth discriminator is gravitational microlensing. A compact mass can bend light from background stars as it passes in front, a consequence of general relativity that has become a practical tool rather than a thought experiment. The star briefly brightens in a characteristic way, even if the lens itself emits no light, because the lens focuses the star's light like a moving gravitational magnifier. The light curve has a symmetry that distinguishes it from many kinds of intrinsic stellar variability, and that symmetry is the clue. Microlensing is powerful because it does not care whether the lens shines. It measures mass through gravity's effect on light, and it can detect dark objects directly, including objects that would never show up in reflected light. It is also difficult because the events are rare and short-lived, and the sky is large, with too many stars to watch casually. The method demands patience, cadence, and an acceptance that most nights will show nothing, which is a hard rhythm for human storytelling. For an Earth-mass to super-Earth-mass lens, the timescale can be hours to days, depending on geometry and relative velocity. The event rate depends on how many background stars you monitor and how much sky you cover, because probability is the currency of the method. The outer solar system adds slow, proper motion, but the lensing geometry still changes and alignments still occur. Even a slow lens can produce a fast event if alignment is tight, because the relevant scale is angular, not emotional. Microlensing also offers something subtle, a way to measure compactness indirectly. A planet with a physical disk can occult light in a different way than a point-like lens, though at these distances the effect is tiny and hard to separate. More importantly, a PBH lens does not come with its own glow, so the baseline is clean, and the event is not contaminated by lens light. That cleanliness is a kind of signature, because it removes one common ambiguity in lensing analysis. A fifth discriminator is close passage dynamics. A PBH is extremely compact, so a small body passing very near can experience strong tidal effects, with differential gravity stretching it along its orbit. A planet has an extended radius and possibly an atmosphere, which changes the near-field encounter outcomes through collisions, drag, and physical capture. The difference is not in the far-field tug, but in what happens when trajectories skim the danger zone and when near becomes literal. In practice, most encounters are not that close, so the difference is subtle and statistical. But a compact object could scatter small bodies in a way that leaves a different distribution of extreme orbits, because bodies can pass closer without hitting a surface. Over long times, the near-field physics could imprint a distinct tail in orbital elements, especially in the most eccentric and most inclined populations. The question is whether we can read that tail from a sparse sample, and whether the solar system has left us enough traces. This is where the chapter reconnects to Chapter 4's emphasis on stability islands. A planet's extended mass distribution is still effectively point-like at large distances, but its physical size matters for collisions and capture, which are the messy details of real systems. A PBH changes the capture and disruption probabilities for objects that graze its Hill sphere, where gravitational dominance over the Sun becomes local. The Hill sphere is the region where the perturber's gravity dominates over the Sun's, and it is where close encounters are negotiated, one trajectory at a time. A planet can sweep up debris, build a family of satellites, and leave behind rings or captured populations because it has a surface and can dissipate energy through impacts and atmospheres. A PBH with no surface and no atmosphere does not collide in the same way, and it cannot catch by contact. Objects that would have struck a planet might instead slingshot around a PBH, or be tidally shredded into streams that later disperse. That difference is not guaranteed to be visible, but it is conceptually sharp, and it changes what companions could mean. The PBH idea also forces a cosmology check because primordial objects come with cosmic bookkeeping. PBHs cannot be invoked freely, because the universe has already been used as a detector, and many experiments have already listened for their fingerprints. If PBHs were too common, they would have shown up in multiple datasets, from lensing statistics to background radiation. The hypothesis is therefore constrained by evidence far beyond the solar system, and that external pressure is part of what makes it scientifically interesting. Microlensing surveys toward the Magellanic Clouds and the galactic bulge already constrain compact dark objects. These surveys were originally motivated by the search for MACOs, massive compact halo objects, as a form of dark matter that could explain galaxy rotation curves without new particles. If PBHs made up most of dark matter in certain mass ranges, the lensing rate would be higher than observed, and the sky would have flickered more often. Those results carve out large forbidden regions in PBH mass and abundance, turning the Milky Way into a statistical laboratory. The history matters here, because it shows how ideas evolve under pressure. In the 1990s, microlensing campaigns watched millions of stars for years, searching for the telltale brightening with careful cadence and meticulous calibration. They found events, but not enough to explain dark matter as a dominant population of compact objects, and the gap mattered. That negative result did not kill PBHs, but it narrowed their allowed role, and it taught astronomers how to measure absence with rigour. The cosmic microwave background adds another constraint, and it is a different kind of measurement. Accreting PBHs in the early universe could inject energy and alter recombination, changing how electrons and protons combined into neutral hydrogen, and how photons decoupled. That would imprint changes in the CMB anisotropy and spectral distortions, which are tightly measured by missions that treat the sky as a precision instrument. The CMB is a fossil photograph, and it is sensitive to small energy leaks, even when the sources are hypothetical. Structure formation adds a third constraint, and it is statistical rather than event-based. Too many PBHs of certain masses would seed small-scale structure differently, changing the distribution of galaxies and halos and altering the smoothness of gravitational potentials. They could add extra granularity to the dark matter field, affecting how matter clumps over time and how early small halos form. The large-scale universe becomes a limit on how many PBHs can exist, even if we never see one directly, because gravity leaves traces in patterns. These constraints do not necessarily forbid a single PBH in our solar system. They limit the cosmic abundance, not the existence of a rare outlier, and rarity is not the same as impossibility. The question becomes whether a PBH of Earth to super-Earth mass could exist without violating population limits, given what we know about dark matter fractions. In other words, can the universe be mostly free of PBHs, while still allowing one to wander into our neighbourhood, like a single stray grain in a clean room? There are still windows where such masses are not completely excluded as a small fraction of dark matter. Even if the allowed fraction is tiny, the solar system could still host one by chance, though the probability becomes a central tension rather than a footnote. The hypothesis is not impossible, but it is not free, and it does not get to ignore statistics. It asks us to accept a low probability capture in exchange for a clean explanation of darkness, and that trade must be weighed. That capture itself invites careful thought, because the solar system is not a vacuum that simply collects objects. For a PBH to become sunbound, it must lose energy, and that usually requires interactions, not just a flyby. It could be slowed by gravitational encounters with planets, or by passing through a dense region in the Sun's birth cluster, where close stellar passages were more common. The details are uncertain, but the requirement keeps the idea grounded, and it prevents the hypothesis from becoming pure atmosphere. The narrative stakes rise here, because the solar system becomes a cosmological laboratory. A confirmed PBH would not just solve Planet 9, and it would not just add a new dot to a diagram. It would be a relic from the first moments of time captured into a sunbound orbit and still orbiting in the cold. It would be a piece of the early universe that never became a star, never became a planet, and never learned to shine. That would connect backyard astronomy to the early universe in a direct way. It would mean the outer solar system is not only a debris field of ice and rock, shaped by migration and collisions. It is a trap that may have caught a fossil of primordial physics, a compact remnant of inflation-era statistics. The familiar map of planets would gain a new kind of object, one that belongs to cosmology more than to geology, and that sits at the boundary of what neighbour means. Visually, the contrast is stark, and it helps to linger on it. Imagine a wide shot of the Kuiper Belt, faint points drifting against a black sea, with the sun a distant glare and the inner planets reduced to a tight, bright knot. Imagine the camera sliding past slow-moving TNOs, each one a cold ember with a long, tilted orbit. Now imagine that the shepherd is not a dim globe, but a compact shadow that cannot be photographed. A mass with no face. The camera would show nothing at the centre, only the choreography of everything around it, as if gravity itself were the actor. But the dread must be handled responsibly, because black holes carry cultural weight. A PBH at hundreds of AU is not a threat to Earth in any practical sense, and it is not a roaming mouth that swallows planets. Its orbit would be stable on long timescales, and its gravitational influence would already be accounted for in the dynamics we observe, because the solar system has been living with the same gravity the whole time. The horror is not physical danger, but the idea that something massive can be present without offering the comfort of light. The horrifying implication is epistemic, not apocalyptic. An object can orbit our sun that does not shine, does not reflect, and barely announces itself, except through subtle, long-term perturbations. It would be a neighbour defined by absence, detected only by the way it moves other things, like wind inferred from swaying grass. The fear is not of destruction, but of ignorance, of how easily something massive can hide, and of how much of our cosmic inventory is built from inference. That implication reframes the infrared whispers from earlier chapters. If the signals are real and repeatable, they lean toward a planet with heat, because thermal emission is hard to fake and hard to sustain without a surface. If the signals fade under scrutiny, the PBH option becomes harder to dismiss because it does not need photons to exist. The same dataset can feel like evidence or like silence depending on what you expect to see, and expectation becomes part of the experiment. So the search strategy must diversify, because one method can be fooled by one kind of darkness. We cannot rely on one wavelength or one catalogue, because a PBH does not play by the usual rules of brightness and colour. We need methods that respond to mass even when light is missing, and methods that can reject false positives with independent checks. The goal becomes redundancy, separate lines of evidence that converge on the same orbit and the same mass, even if the object remains visually absent. Microlensing becomes a primary tool. Monitor dense star fields and look for transient brightening with the right symmetric light curve, then test whether the event's duration implies an Earth mass lens rather than a star. Reject stellar variability in instrumental artifacts through cadence, colour information, and repeat statistics, because the sky is full of imposters. The work is less like taking a picture and more like listening for a brief change in volume, where the signal is a curve that appears and disappears. The observational choreography is demanding, and it shapes the visuals of the story. You would see a grid of stars, then a single star swelling in brightness and returning to normal, with no visible culprit drifting into frame. There is no shadow crossing the star, and no object revealed by contrast, only a rise and fall that can be fit by a lensing model. The curve on a graph becomes the character, rising and falling like a heartbeat, and the mass is inferred from timing. Accretion searches become a secondary tool because they depend on environmental luck. Look for faint localized X-ray or radio sources that move slowly against the sky, consistent with a distant solar orbiting object rather than a distant galaxy. Cross-match with infrared and optical catalogues to rule out ordinary stars, active galactic nuclei, and background transients. If a source has no counterpart and shows the right motion, it becomes suspicious, and suspicion becomes a target list. Dynamical searches remain the backbone, because they are what started the mystery. Use the growing TNO sample to map scattering patterns and resonant structure, then ask whether a single perturber explains them coherently across multiple subpopulations. Test whether the distribution prefers a point-like perturber with no extended physical interactions, or whether it hints at collisions and capture that imply a planet. The more objects we discover, the more the statistical picture sharpens, and the less room there is for storytelling without math. The key is that a PBH is the extreme limit of compactness. If the data eventually demand a perturber that behaves like a point mass down to very small scales, the PBH hypothesis gains weight, because it is the cleanest point mass nature allows. If the data reveal a thermal emitter with a radius, the PBH hypothesis collapses, because radius is a surface and a surface is a planet. The story is therefore balanced on what kind of body the evidence insists on, and on whether the universe lets mass exist without a face. The chapter also clarifies what would count as a decisive detection, because ambiguity is the enemy of narrative. A planet can be confirmed by repeated imaging and orbit fitting, where the same moving source returns night after night, and its path predicts its next appearance. A PBH can be confirmed by microlensing plus consistent dynamical mass inference, even without direct photons from the object, because gravity can be measured twice. The confirmation would be mathematical first, visual second, and that inversion is part of the unease. That is a different kind of astronomy than the public expects. It is astronomy where the object is defined by its gravitational footprint on light and on orbits, and where detection can mean a distortion rather than a dot. It is closer to how we infer dark matter than how we discover planets, and it borrows the same humility. It asks us to accept that seeing can mean measuring a subtle change in brightness or a slow drift in orbital elements, and trusting the inference. This is why the Planet 9 story belongs in a cosmology-forward chapter. The outer solar system is not just the edge of planetary science, where the sun's warmth fades and ice dominates, and where the sky feels empty. It is a testbed for ideas about the early universe and the inventory of compact dark objects, because the same gravitational rules apply locally and cosmically. It is where local dynamics and cosmic history can intersect, and where a single captured relic could connect the solar system to inflation-era physics. The central question returns with sharper edges, because the options are no longer just big planet or no planet. Are the infrared signals and strange outer, solar system orbits evidence of a real Planet 9, a cold world with a surface and a spectrum, obeying the usual rules of planetary light? Or are we seeing something far stranger, like a primordial black hole, reshaping the edge of our solar system while refusing to be photographed? If the latter is true, what else have we assumed must shine, and how many other inferences rest on that assumption? The answer will not come from one dramatic image, because a PBH offers no postcard view. It will come from survey power, cadence, and statistical certainty across millions of sources, where rare events become measurable through repetition. It will come from turning whispers into repeatable events, and from treating the sky as a time series rather than a snapshot night after night. The decisive moment may be a curve on a plot, not a dot in a frame, and the proof may feel more like physics than like photography. That requirement sets up the next transition, because it points to a specific kind of instrument and a specific kind of era. Whether it is a planet or a black hole, detection demands a new kind of sky coverage and a new flood of time domain data. The Rubin era is where that flood begins, and where the outer solar system will finally be watched like a living system. The hunt has always been limited by two stubborn facts, and neither one cares about our patience. The sky's enormous, and the suspected object moves like a slow leak across it. Even when you know where to look, the target refuses to behave like a target. It behaves like background, nearly star-like, nearly stationary, and almost perfectly willing to be ignored. Earlier chapters built a case from two fragile pillars, and both were easy to shake when pressure arrived. Infrared catalogues offered whispers near the noise floor, where calibration quirks, blended sources and cirrus confusion can impersonate planets. Extreme TNO orbits hinted at a persistent sculptor, yet bias arguments stayed plausible because the discovery record was uneven. For years, the debate lived in that uncomfortable middle zone, interesting enough to pursue, uncertain enough to doubt, and resilient enough to survive every attempted dismissal. By 2025, the search changes character. It stops being a patchwork of narrow surveys and becomes a time domain machine. The Vera C. Rubin Observatory begins the legacy survey of space and time, and the outer solar system becomes a monitored system. The shift is not philosophical, it is mechanical, and it is statistical. A monitored system is one you can audit, night by night, field by field, with a paper trail of what was possible. Rubin is not one deeper image, and it is not one heroic exposure taken under perfect seeing. Rubin is repeated imaging that turns still photos into motion, and motion into a measurable signature. Its wide field maps huge sky area quickly, then returns again and again with planned cadence. Those revisits are scheduled, logged, and predictable, so the absence of a detection becomes almost as informative as a detection. Visually, Rubin's camera is like a tiled mosaic of the night, a focal plane packed with sensors that behave like a single, giant eye. A single pointing captures a broad swath of stars, galaxies, and faint smudges, while the telescope's cadence stitches those swaths into a living atlas. Night after night, the same regions are revisited, and the sky begins to behave like a dataset rather than a mystery. In the control room, the sky is not only observed, it is versioned. The survey focuses on the southern sky, but its impact is global because the analysis is portable and the catalogue is shared. It builds a uniform dataset with known cadence, known depth, and known gaps, and those gaps matter. That uniformity is what the Planet 9 debate has lacked, because past searches were often opportunistic. They were driven by available telescope time, seasonal constraints, and shifting priorities, so the footprint itself became a suspect. Cadence is everything for slow movers, and the outer solar system is the realm of slow movers. A distant object can look like a star in a single visit, because its light is steady and its point spread function is ordinary. Only revisits reveal drift, curvature, and parallax that cannot be faked by static backgrounds. In other words, time is the instrument, and the calendar becomes part of the optics. At hundreds of AU, apparent motion is tiny, and the numbers are humbling in a way that rewrites intuition. The object's proper motion is measured in arc-seconds over weeks, not minutes, and that means it can hide in plain sight. Parallax from Earth's orbit adds a second signature that repeats with geometry, and that repetition is crucial. A real solar system body shifts with the seasons in a way a distant galaxy cannot, even when both look like identical points. It helps to picture the geometry in 3 dimensions, because the effect is simple, but the consequences are not. Earth moves around the Sun, and our viewpoint slides across a baseline of 2 astronomical units. Against the far background, a nearby object seems to wobble, an annual loop whose size shrinks with distance. That wobble is small at hundreds of AU, yet it is coherent, and coherence is what algorithms can exploit. The loop is not artistic, it is a fingerprint. Earlier surveys struggled because they were not designed for this rhythm. Even when they were technically superb, they were deep but narrow, or wide but shallow, or irregular in revisit timing, and those trade-offs were not mistakes. They were optimized for other science goals, like distant galaxies, supernovae, or near-Earth asteroids that move quickly. They found objects, but they could not easily link them across time, especially when detections were sparse and separated by months. Rubin's depth matters, but repetition matters more, because repetition turns chance into statistics. Each visit reaches faint magnitudes, then stacks into still deeper coids, and the sky slowly fills with objects that were previously invisible. The key is that Rubin also preserves the time series, not only the final stacked image. That preservation is an architectural decision, one that treats variability and motion as first-class data products, rather than as inconvenient leftovers. The time series enables motion mining, which is the quiet engine of this chapter, and the real reason 2025 is different. The pipeline searches for transient points, then tries to link them into tracks that make physical sense. It is not one detection that matters, but a consistent chain that survives scrutiny. In practice, this means measuring positions, uncertainties, and how those uncertainties propagate through time, because error bars are part of the orbit. Motion mining begins with difference imaging, a technique that turns the static sky into a subtraction problem. Subtract a reference sky, and new points appear as residuals like sparks on a dark canvas. Most residuals are junk, cosmic rays, detector artifacts, imperfect subtractions around bright stars, and subtle ghosts from optics. The software learns to reject them, and the learning is guided by labelled examples and by physics-based expectations. It is quality control at planetary scale. A vivid way to imagine difference imaging is to picture 2 nearly identical photographs taken weeks apart. When you subtract them, the unchanging stars cancel out, and what remains is change itself. That change can be an exploding star in a distant galaxy, a variable star in our own, or a faint dot that has shifted by a fraction of a pixel. Rubin's challenge is to separate those categories at scale, millions of alerts, with only a few that matter. The next step is linking, where the pipeline tries to decide whether 2 detections are the same object seen at different times. Detections from one night are paired with later nights using plausible motion models, and those models are constrained by celestial mechanics. The algorithm must tolerate missing nights, weather gaps, and fields that were not observed. It must also tolerate the fact that faint detections have larger positional errors, which can make a real object look inconsistent. Linking is not just bookkeeping, it is a combinatorial problem, because the sky contains countless transient-like residuals, and many of them can be paired incorrectly. The pipeline uses constraints, maximum plausible rates, expected directions, and the smoothness of motion to prune the search. When it works, a scattered set of points becomes a trajectory, and a trajectory becomes a candidate orbit. The triumph is quiet because it happens inside a database. For very slow and faint objects, standard linking can fail, and the failure is predictable rather than embarrassing. The object is below single-visit detection, so it never appears as a clean point in any one image. That is where shift and stack becomes the decisive trick, and it is a trick born from patience. Instead of asking for a dot in one frame, you ask whether a dot exists across many frames, hidden but consistent. Shift and stack assumes a trial motion vector, which is a guess about how the object moves across the detector between exposures. Images are shifted along that vector and stacked, so a moving object adds coherently, and noise averages down. Background stars smear out, and the hidden point can rise above noise. If the guess is wrong, the object smears too, and nothing appears. In effect, you are scanning through possible futures until one aligns with reality. Visually, this is one of the most satisfying moments in the hunt, because it feels like the sky finally cooperates. A sequence of frames looks empty, or at least indistinguishable from random speckle and faint galaxies. Then, after the correct shift, a faint, steady point condenses out of the grain, like a face emerging in a developing photograph. The emergence is statistical, but it feels like revelation, and it is earned by repetition. This is computationally expensive because the space of possible motion vectors is large and the sky coverage is enormous. You must test many speeds and directions, and you must do it across huge areas of sky. Rubin is built for data-scale astronomy, and that scale is not a metaphor. The observatory produces a flood of pixels, and the science depends on turning that flood into catalogues, alerts, and measured uncertainties. The telescope is a camera, but the discovery engine is a pipeline. Planet 9 becomes a software problem as much as an optics problem, and that is a historical change in how discovery happens. In earlier eras, discovery was often constrained by photographic plates, human scanning, and limited computing, with astronomers literally blinking images by eye. Today the bottleneck is often algorithmic design, compute allocation, and reproducible pipelines. The modern hunt is conducted as much in code repositories as under domes, and the audit trail is part of the claim. Shift and stack also changes what signal means in the Planet 9 era, and it changes what counts as persuasive. A candidate is no longer one faint dot in one catalogue, vulnerable to a single bad pixel or a subtraction artifact. A candidate becomes a statistically significant detection across many nights, consistent with a single orbit. The evidence is distributed across time, and that distribution is harder to counterfeit. You are not trusting one image, you are trusting a pattern. Rubin can do what earlier surveys could not, and it does it repeatedly, which is the crucial word. It pushes to fainter limiting magnitudes across wide area, and it returns to those areas on a cadence that supports orbit building. It also measures its own selection function in detail, because the survey strategy is documented and stable. That stability is not glamorous, but it is decisive, because stability makes null results interpretable. Selection function sounds abstract, so it helps to translate it into something you can picture. It is the map of what the survey is capable of finding and where it is blind. It depends on sky brightness, seeing, air mass, star crowding, and even the moon's phase. It also depends on how motion interacts with exposure time, because a fast object can trail and lose detectability. Without that map, absence of evidence becomes ambiguous, and ambiguity is where debates live. That matters because bias has been the defense against every clustering claim, and it has been a serious defense. Critics argue that discovery footprints manufacture alignment, and they have a point worth respecting. If you only search certain longitudes, you will preferentially find objects there, and patterns can appear. Rubin turns that critique into a measurable parameter rather than a rhetorical veto. The argument becomes quantitative: how much alignment survives after you model the search itself. With Rubin, you can inject synthetic objects into the pipeline, and you can do it at scale without guessing. You can ask which orbits would be found and which would be missed, then compare the recovered sample to the injected truth. You can quantify how cadence, sky brightness, and star crowding shape the final sample. The argument moves from maybe to how much, and that shift is the real turning point. This is the turning point for the orbital argument, because it forces the models to face calibrated data. If clustering survives after bias correction, it becomes harder to dismiss, and the gravitational sculptor gains credibility. If it collapses, the Planet 9 corridor dissolves into ordinary selection effects, and the mystery changes shape. Either outcome is valuable, because it ends a certain kind of uncertainty, and replaces it with a measured constraint. Rubin also expands the sample size brutally, and that brutality is the point rather than a side effect. The extreme TNO population grows from dozens to hundreds, then to thousands, and the distribution begins to look like a distribution. Small number statistics stop being an excuse, and dynamical models face real shapes, tails, and correlations. When the sample is large, the outliers become meaningful rather than merely intriguing, and the weird ones become a class. There is also a subtle benefit of scale that is easy to miss when you focus on the headline planet. With many objects, you can test whether the population is internally consistent, or whether it is stitched together from incompatible subgroups. You can ask whether the detached objects share a common history, whether resonant objects cluster in expected islands, and whether inclinations follow the predicted spread. The outer solar system becomes less anecdotal and more like ecology. This is where 2023 KQ-14 returns to center stage, not as a celebrity but as a test case with leverage. Its orbit needs refinement, and Rubin's astrometry extends arcs quickly because repeated visits accumulate positional measurements. A longer arc tightens semi-major axis and orientation, which tightens every integration. In orbital mechanics, uncertainty is not a nuisance. It is a force that spreads predictions, and it can manufacture false confidence. Astrometry sounds like a simple act. Measure where something is, but it is precision work with hidden complexity. The position of a faint point must be tied to a reference frame, corrected for optical distortions, and expressed with uncertainties that are honest. Atmospheric turbulence shifts centroids, and detector effects can bias positions by tiny amounts that still matter. Rubin's repeated measurements allow those uncertainties to shrink, and shrinking uncertainties are what make dynamical claims testable. If KQ-14 is truly resonant or detached, Rubin will find neighbours, and neighbours change the story in a way a single orbit cannot. Resonant islands should contain multiple occupants, not one lonely survivor, because resonances are dynamical structures that trap and protect. A single object can be a fluke, but a family becomes architecture. Architecture implies a builder, whether that builder is a planet, migration history, or something else that acted for millions of years. Rubin also tests the predicted high-inclination population, which is one of the more dramatic consequences of Planet 9 models. Many simulations generate tilted and even retrograde objects, bodies whose orbital planes are steeply inclined to the ecliptic. Those are hard to find in ecliptic-focused surveys, because the searchlight is pointed in the wrong direction. Rubin's footprint and cadence make them less invisible, and its uniformity makes them harder to argue away. High-inclination objects are also a diagnostic because they are difficult to produce in large numbers. Scattering by the known giant planets can excite inclinations, but the most extreme tilts may require additional long-term perturbations. If Rubin finds a substantial retrograde component among distant objects, the dynamical conversation changes. If it does not, certain versions of the Planet 9 hypothesis weaken, and the allowed parameter space narrows. The hunt is not only optical, and it never has been, even when the public story focuses on visible light images. NASA assets and infrared archives remain essential, because a cold planet should glow thermally even when it reflects little sunlight. Rubin provides tracks and ephemerids that can be cross-matched to infrared sources, and that cross-match is a powerful filter. It turns a crowded infrared sky into a targeted question. Does anything at this moving position emit the right kind of heat? Infrared catalogues like WISE and NeoWISE already map the sky, but confusion is severe, especially near the galactic plane and in regions of cirrus. Galaxies, dust filaments, and instrumental artifacts create false candidates, and faint sources can be blended into one catalogue entry. A moving optical track can separate a solar system body from a background galaxy, because galaxies do not share our parallax. Motion is the discriminator that infrared alone often lacks. Cross-matching works in both directions, and that symmetry matters because it reduces the chance of self-deception. An infrared candidate can be tested against Rubin time series for motion, and a Rubin moving object candidate can be checked for infrared colour consistent with tens of Kelvin emission. A cold planet's thermal spectrum would peak in the mid to far infrared, while reflected light dominates in the optical. The ratio between them encodes size and reflectivity, and it can break degeneracies that brightness alone cannot. This is how the infrared whisper becomes a measurement, or becomes a non-detection with teeth. A true planet should show consistent thermal flux across epochs, within model expectations, and it should shift position in a way that matches the optical orbit. A galaxy should not move, and its colours should betray its distance through red-shifted starlight and dust. Consistency across instruments is the enemy of coincidence, and coincidence is what false candidates live on. NASA's role is also strategic, because space-based infrared avoids atmosphere and provides stable calibration over long baselines. Archival surveys become a time machine, extending the observational arc backward once Rubin provides a precise predicted position. A faint object that is hard to detect in a blind search can become obvious when you know exactly where to look. This is how old data gains new power, and how a modern survey can resurrect photons collected a decade earlier. There is a historical echo here, because solar system discovery has always depended on hindsight. Many objects have been pre-covered in archival images, sometimes years before their official discovery, because they were too faint or too slow to be noticed. Clyde Tombaugh's era relied on careful plate comparisons, and even then, the sky held unrecognized motion. The difference now is systematic capability. Rubin's ephemerides can guide a targeted archival search, and that targeted search can provide early points that dramatically tighten the orbit. A confirmation sequence has a specific shape, and it is more procedural than cinematic, which is why it is trustworthy. First comes repeated detection and a linked track, which establishes that the object is real and moving. Then comes orbit fitting that predicts future positions with shrinking uncertainty, and those predictions are the heart of confirmation. A real object continues to appear where the model says it will, and the model improves because it keeps being right. The key is arc extension, because short arcs can lie in ways that feel convincing. A few nights can fit a rough orbit, but months and years reveal curvature, and curvature is where distance hides. Parallax and proper motion must be consistent with a distant heliocentric orbit, not a near-Earth interloper or a main belt asteroid that only looks slow. The outer solar system announces itself through slowness and through the stubborn regularity of seasons. In practical terms, orbit fitting is an exercise in probability, not just geometry. The pipeline explores families of orbits that could explain the data, then narrows them as new points arrive. Early on, the uncertainty region on the sky can be large, and recovery is difficult, especially near crowded starfields. Later, the uncertainty collapses into a small patch, and follow-up becomes efficient. The story turns from searching to checking. Once ephemerides are reliable, follow-up becomes targeted rather than hopeful, and that changes the emotional texture of the hunt. Large telescopes can recover the object at predicted positions, and independent teams can confirm motion, reducing the chance of pipeline artifacts. This independence is not bureaucracy, it is error control. In astronomy, a claim becomes real when it survives other people's instruments, other people's reductions, and other people's skepticism. Then comes characterization, where the discovery turns into a physical object rather than a dot with coordinates. Multiband photometry constrains color and phase behavior, which hints at surface composition, grain size, and possible haze. If thermal flux is measured, size and albedo can be disentangled, because brightness in reflected light alone cannot tell you both. A dark large body can mimic a small bright one, and nature does not label its variables. The phase curve, the way brightness changes with viewing geometry, adds another layer of constraint. Icy surfaces, dusty regoliths, and hazy atmospheres scatter light differently, and those differences show up as subtle trends. At great distances, the phase angles are small, yet even small angles can carry information when measured precisely across filters. The point is not drama, it is constraint, and constraint is how you turn a hypothesis into a world. Temperature estimates matter because they connect to internal heat, and internal heat connects to origin and composition. A super-Earth mass planet may retain formation energy and radiogenic heat, and that heat can persist for billions of years. That heat changes infrared brightness and changes the expected detectability window, especially in mid-infrared bands. A slightly warmer planet is far easier to see in thermal emission, and that difference can decide whether silence is meaningful. There is also the question of atmosphere, which is implied by some models but not guaranteed by distance alone. At tens of Kelvin, common volatiles can freeze, collapse, or form exotic ices, and atmospheric chemistry becomes unfamiliar. Would such a world be a scaled-up Pluto, or something closer to a mini Neptune with a cold, tenuous envelope? Rubin cannot answer that alone, but it can provide the target, precise enough for the next instruments to interrogate. Spectroscopy is hard at these magnitudes, but it is the prize, because spectra turn light into chemistry. Even low-resolution spectra can separate methane-rich atmospheres from featureless dark surfaces, and they can reveal absorption bands of water ice or complex organics. A spectrum also helps rule out exotic imposters, because imposters have different energy distributions across wavelengths. The faintness makes it difficult, yet difficulty is not impossibility when the ephemeris is good. If the culprit is not a planet, Rubin still matters, and the narrative does not collapse into disappointment. A primordial black hole would not reflect sunlight or glow thermally in a way we can easily detect. Yet it would still reveal itself through gravity acting on light and on orbits, and gravity is Rubin's indirect instrument. The outer solar system is a laboratory for long-term perturbations, where small tugs accumulate into measurable architecture. Microlensing becomes the cleanest direct test of a dark compact mass, because it does not require emitted light at all. Rubin watches dense starfields repeatedly, and it can detect transient brightening events when a lens passes near the line of sight. Event statistics can constrain the presence of a compact lens in the outer solar system. The method is rare event astronomy, but Rubin is built for rare events, and its cadence turns rarity into a searchable pattern. A single microlensing event is not a full identification, and it would not end the story by itself. The sky produces many lensing events from ordinary stars, and the background is busy and uneven. The key would be an event consistent with a nearby slow-moving lens, with parallax effects that imply solar system distance. The light curve shape, duration, and asymmetry would carry the clue, and the clue would be subtle. Rubin can also search for dynamical oddities that favour compactness, and the logic is subtle enough to feel almost forensic. A black hole allows extremely close flybys without collision, because there is no physical surface to hit. Over time, that could produce a tail of extreme high-velocity orbits among small bodies, and those orbits would look like scars. The scars would be statistical, not singular, and they would emerge only when the catalogue is large. Those signatures demand a large catalogue, and they demand consistent astrometry and consistent bias modelling across the survey footprint. Rubin provides that catalogue, and it provides it with a survey design that can be simulated and tested. The same dataset tests Planet 9 and tests the darker alternative, which is why this chapter is about infrastructure. Infrastructure is what allows multiple hypotheses to be evaluated honestly, without switching standards midstream. The cultural layer matters because it changes how fast the hunt iterates and how quickly errors are caught in public view. Rubin's data releases are public on planned schedules, and the community will build tools around that predictability. Planet 9 becomes a shared data set, not a private treasure map. Shared data changes incentives because it rewards verification as much as discovery, and it makes quiet corrections possible before loud claims harden. Citizen science has a real role in time-domain astronomy, and it is not just romantic outreach pasted onto serious work. Volunteers can flag odd motion, odd variability, and pipeline failures, especially in edge cases where algorithms struggle. Public participation also increases scrutiny, which reduces the chance of a false triumph. In a field where a single artifact can masquerade as a discovery, scrutiny as a feature and curiosity becomes labour. The modern space documentary ecosystem amplifies this feedback loop, and it does so instantly, sometimes uncomfortably. Planet 9 is a top-tier mystery across channels, from quick compilation formats to long-form features that mimic classic expedition narratives. That attention can distort expectations, because audiences want reveals and villains and clean endings. Yet it also sustains follow-up pressure, because interest keeps the question alive between data releases, when the work is mostly waiting and reprocessing. The risk is that hype outruns uncertainty, and the Rubin era will test that risk repeatedly. A candidate point source can go viral before it survives basic checks, and the internet rewards speed over caution. Rubin's era will produce many candidates, and most will die under reanalysis, because the pipeline is designed to be generous at first. The honest story is not the first detection. It is the last surviving one, the one that keeps returning on schedule. The responsible story is about process, and process is not a downgrade from wonder. A real discovery is not one screenshot, but a chain of predictions that keep coming true, across seasons and instruments. The public will have to learn to wait for orbit closure, not just first light. That waiting is part of what makes science different from rumour, and it is part of what makes the eventual answer durable. Voyager and Voyager 2 remain quiet narrators in this chapter, drifting at the edge of our awareness like distant lanterns. They crossed the heliosphere boundary and measured a changing plasma environment, where solar wind yields to interstellar pressure. Their instruments, built for a different era, still report on magnetic fields and particles. Their data remind us the solar system is a dynamic bubble moving through the galaxy, not a static diagram in a textbook. That context matters for Planet 9, because it reframes what edge means in more than one sense. The heliosphere is a physical boundary shaped by plasma and fields, while the gravitational boundary is shaped by mass and time. A distant massive object would be another boundary marker, a gravitational landmark beyond the known planets. It would reshape how we define the solar system's architecture, not only its edge, and it would invite a new question. What else have we assumed is empty? Rubin's survey turns that architecture into a testable map, and the map is both what we see and what we miss. It measures what we can see, and it measures what we miss, because the misses are encoded in the selection function. It converts the bias debate into a calibration problem, and it converts whispers into time series. A time series can be interrogated, replicated, and reprocessed. which is why it changes the tone of the argument. The climax is not a reveal yet, and that restraint is part of the suspense rather than a denial of it. The climax is the moment the search becomes capable of ending the argument, one way or the other. For the first time, the sky is watched with the cadence that the mystery demands. The hunt stops being a collection of heroic efforts and becomes a systematic watch, an instrument pointed not at a spot, but at time itself. If Planet 9 exists, Rubin should either see it directly or corner it through the population it shepherds, because shepherding leaves patterns. If a black hole is responsible, Rubin should constrain it through microlensing and through the statistics of extreme orbits. Either way, the dataset becomes a lever that moves the debate. The lever is long, and it is built from repeated nights, repeated calibrations, and repeated chances to be wrong. Either outcome changes the meaning of the earlier infrared hints, and it changes what silence means when the sensitivity is known. A confirmed thermal emitter turns the whisper into a world, with mass, temperature, and a place in the family portrait. A continued infrared silence, paired with strong dynamical evidence, makes the darker option harder to ignore. Silence can be a measurement when you know how loud the signal should be, and when you can show your work. We end with the apparatus finally in place, and the tone shifts from speculation to test. The new sky is not just deeper, it is repeated, searchable, and accountable, and accountability is what mysteries fear. The edge of the solar system is about to become a measured environment, with catalogues that can be challenged and improved. The hunt becomes less like folklore and more like metrology, and that is how the unknown becomes ordinary. Now we return to the core question. What is most likely, what is most revolutionary, and what would each answer mean for Earth's place in the solar system and the cosmos? We arrive at the edge again, where sunlight is a rumour and motion is patient. The camera drifts past a sparse field of stars, and the foreground emptiness feels almost staged. Out here, distance is not a number but a delay. Light takes hours to cross the inner system, and days to reach the farthest probes. The central question stays simple and sharp, even as the data grows complicated. Are the signals and orbits pointing to Planet 9, or to something stranger? 3 threads have carried the story through the dark, and each thread has its own physics. Orbital clustering suggests a shepherd that talks distant bodies over millions of years, nudging their perihelia and longitudes into a shared geometry. Akari's infrared candidates suggest heat where a hidden world should drift, because even a cold planet must re-radiate absorbed sunlight. 2023 KQ-14 suggests dynamical structure that may not survive without an extra mass, as though the outer system has an unseen load-bearing beam. Each thread alone is suggestive, and each thread alone can mislead. Clustering can be manufactured by footprint, cadence, and follow-up bias, because we do not scan the sky like a perfectly even paint roller. Infrared points can be galaxies, cirrus knots, or artifacts near the noise floor, especially when the background is textured by interstellar dust. A single new etno can look decisive until the sample grows and the pattern shifts, because rare objects exaggerate whatever trend we want to see. The deeper issue is that the outer solar system is not a laboratory bench. We cannot move the test masses, and we cannot rerun the early solar system with different initial conditions. We only inherit the outcome, then try to infer the forces that shaped it. That is why these threads matter. They are different instruments touching the same invisible object. Together, the threads become harder to ignore, because they constrain each other. Dynamics narrows the sky corridor, and predicts what kinds of orbits should exist, including which resonances would be populated and which inclinations would be excited. Infrared candidates offer specific coordinates that can be tested for motion and colour, rather than a vague promise that something might be out there. KQ-14 adds a new angle and a new timescale, tightening the corridor or breaking it, because its stability depends on the long-term gravitational landscape. In visuals, this synthesis is a braid. One strand is orbital geometry, drawn as pale ellipses on a black plane. Another strand is infrared sky maps, mottled with faint structure and punctuated by tiny points. The third strand is a single object arc, short, uncertain, and yet heavy with implication. When the strands align, the braid looks like a corridor through the constellations, a narrow path cut through an otherwise overwhelming search space. The synthesis is not a verdict, because science does not reward narrative closure. It is a weighted comparison of explanations that survive contact with data, and the weights change when new surveys arrive. Planet 9 remains a best fit in many integrations, but best fit is not the same as real. A model can be elegant and still be wrong, especially when the sky is undersampled. Scientists use probability words in a precise way, and the precision matters here. A best fit model is the parameter set that minimizes mismatch to the current sample, given an assumed selection function and an assumed dynamical history. Confidence is the fraction of simulated worlds where the pattern would appear by chance, after accounting for how many patterns were tested. Both depend on assumptions about bias, completeness, and the look elsewhere effect, which is the quiet penalty for searching many corridors until one looks meaningful. Small number statistics are a trap because extreme objects are rare and hard to find. At hundreds of AU, discovery happens near perihelion, so the catalogue is geometry heavy and seasonally biased. A few detections can swing angles and significance because the phase space is huge and the sky coverage is patchy. The honest posture is provisional, even when the pattern feels persuasive, because persuasion is not a statistical operator. There is also a timescale problem that hides inside the math. These orbits take thousands of years to complete, so we see only a tiny fraction of each path. Orbit fitting becomes a game of inference from short arcs, where uncertainties in distance and inclination can masquerade as structure. The outer solar system rewards patience and it punishes overconfident extrapolation. Absence of confirmation is not disproof, and that is not a loophole. The search volume is enormous, and the target is slow, faint, and possibly off the ecliptic, where many surveys historically spent less time. A planet at 600 AU can hide among background stars for months because its apparent motion is measured in arcseconds per hour. A PBH can hide without emitting anything at all because it offers gravity and little else. This is why certainty is slow. Even in the era of powerful surveys, you do not confirm a distant world with one frame, or even one season, because a single detection can be a cosmic ray, a moving asteroid, or a transient artifact. You confirm it by repeated recovery, orbit closure, and cross-instrument consistency, until the object behaves like a coherent body and not a statistical accident. Time becomes evidence, because time forces predictions to keep coming true. Now the evidence threads can be restated as testable predictions, not just hints. If a planet is sculpting etnos, new objects should populate resonant islands and high-inclination tails, including populations that are hard to create with Neptune alone. If Akari's candidates are real, they should show measurable parallax and proper motion shifting against the star field as Earth moves around the Sun. If KQ-14 is part of a coherent architecture, its refined orbit should align with a stable dynamical family, rather than wandering into instability when the integrations are extended. The predictions also have a texture that can be visualized. Resonant islands are not poetic language. They are phase-space neighborhoods, where orbital periods lock into ratios. High-inclination tails are not a metaphor. They are literal tilts that carry objects far above the ecliptic plane. Parallax is not just a word, it is the annual breathing of perspective that turns a point into a distance. These are the handles that let astronomers grab the problem. Rubin turns these predictions into a decision tree, because Rubin is cadence plus uniformity. Its wide field repeatedly images the same regions, and its pipeline is designed to treat the sky as a time series rather than a scrapbook. It measures what it sees, and it measures what it could have seen, which is the crucial difference between discovery and inference. That selection function is the antidote to the bias argument, because it makes bias quantifiable rather than rhetorical. Historically, this is the pivot the outer solar system has waited for. The discovery of Pluto in 1930 came from a targeted hunt and a blink comparator, not from a uniform digital census. The Kuiper Belt's modern era began in the 1990s, when CCDs made faint moving points accessible, yet coverage was still uneven and follow-up was expensive. Each generation found new worlds, but each generation also inherited the same accusation. Maybe the pattern is just where we looked. Rubin is built to answer that accusation with numbers. First branch. Rubin finds a moving object with the right slow drift and annual parallax, and the motion is consistent across nights and seasons. Its orbit fits the dynamical corridor implied by ETNOS and by KQ-14's stability constraints, landing in the region where simulations say a shepherd could reside. Its brightness and colour are consistent with a cold, distant planet, perhaps with methane or nitrogen-rich ices that redden under radiation. Planet 9 becomes real, because the model stops being an inference and becomes a tracked body. On screen, the moment is quiet rather than explosive. A faint dot is circled, then circled again in a later frame, and the separation is small but undeniable. A line appears between positions, then a curve, then an ellipse as the orbit fit tightens. The dot graduates into a marker with an ephemeris, and the ephemeris becomes a promise that can be checked. In astronomy, that is what reality looks like: repeatability. Second branch. Rubin does not find the planet, but it finds many new TNOs, and the catalogue expands from dozens to hundreds in the relevant regime. The expanded sample erases clustering once the survey footprint is modelled, because the previously empty regions fill in with objects that were simply missed. The apparent alignment dissolves into selection effects and follow-up history, and the corridor becomes a mirage drawn by our own observing habits. The story becomes a lesson in how the sky can fool us, when we only see what we can reach. This branch is not failure, even if it feels like it. It would mean the outer solar system is still rich, but rich in a different way, with structure driven by Neptune, stellar passages, and the slow diffusion of orbits over time. It would also be a methodological victory, because it would show that the community can quantify bias rather than argue about it. The universe would not be obliged to provide a hidden planet, and science would not be diminished by that refusal. Third branch. Rubin and follow-ups find signatures that favour a compact dark mass, and the evidence arrives sideways through gravity. A microlensing event appears with the right symmetry and timescale for an Earth to super-Earth lens, a brief amplification as a foreground mass bends background starlight. The lens shows no optical or infrared counterpart, despite deep targeted searches that would reveal even a very cold planet. The PBH hypothesis gains ground because gravity is detected without a surface. Microlensing is subtle, and the subtlety is part of its power. The light curve rises and falls in a smooth, time-symmetric way, and the peak is not a flare but a geometry. The timescale encodes the lens mass and relative motion, while the shape constrains the impact parameter. In plain language, the sky briefly tells you that something passed in front, even when the something is invisible. These branches are not equal in drama, but they are equal in scientific value. Any branch would redraw the map of the outer solar system, because each outcome forces a different accounting of mass and history. Any branch would turn a long debate into a constrained result, replacing speculation with measured populations or measured trajectories. The difference is what kind of object the result forces us to accept, and what kind of story we must then tell. Planet 9, if confirmed, would be a new class of local world. It would sit between ice giants and super-Earths in mass, but in a solar orbit far beyond the classical planets that shaped our childhood diagrams. Its existence would demand a formation and migration story that survives dynamical accounting, not just an appealing narrative. It would force models to explain how a massive planet ended up so far out, and how it avoided being ejected entirely. One pathway is scattering followed by damping, perhaps in the Sun's birth cluster, where gas and passing stars could soften a violent trajectory. Another pathway is capture during early stellar encounters, when the Sun was not alone and gravitational exchanges were more common. Another pathway is in situ formation in a massive extended disk, which strains standard disk models because solids thin out with distance. Each pathway changes how we think planets assemble, and how often systems hide distant members. There is historical weight behind these pathways, because the solar system has revised itself before. Uranus was discovered in 1781 as a new planet, and Neptune in 1846 was inferred from perturbations before it was seen, a triumph of dynamics over darkness. Pluto followed as a misdirected solution to a mass problem, then became the doorway to the Kuiper Belt, which turned out to be the real story. Planet 9 would join that lineage, an object found at the boundary between prediction and surprise. A distant planet also blurs a boundary we pretend is clean. We call some bodies planets because they orbit our sun, and exoplanets because they orbit other stars, as though the physics changes at the heliopause. A super-Earth in our own outskirts would make that distinction feel parochial, even slightly embarrassing. It would remind us that the solar system is not a closed museum, but one example among many architectures. The exoplanet connection is not rhetorical, it is methodological. We infer many exoplanets from indirect signals, including transits and radial velocities, and we accept them because the signals repeat and the models predict. Planet 9 would be an indirect discovery made local, then made direct by persistence, which is a rare chance to test inference against a resolved object. It would validate the logic of inference, while exposing how hard it is to confirm faint worlds even in our backyard. If the PBH branch strengthens, the implications widen further, and the tone of the story changes. A primordial black hole would connect the solar system to early universe physics, because such objects would form from density fluctuations long before stars existed. It would be a relic older than the Sun, captured into a bound orbit, and its very presence would be an archaeological find. It would force a probability reckoning, because capture requires energy loss, and cosmology constrains abundance. That probability tension would not kill the idea, but it would shape the conclusion. A single PBH could exist even if PBHs are a tiny dark matter fraction. Because rare does not mean impossible in a galaxy with billions of systems. The question would become how the Sun's birth environment enabled capture, perhaps through multi-body interactions that bleed orbital energy. The outer solar system would become a laboratory for rare events, not just for planetary leftovers. Whether planet or PBH, the horrifying framing needs honesty. There is no imminent danger to Earth from a distant perturber on a stable orbit, and stability is the key word that the fear often ignores. The solar system has already lived with its gravity for billions of years, and the inner planets are not suddenly at risk. The unease is existential, because it means a major mass can remain unseen in our own neighbourhood, and our confidence is revealed as a local comfort. The horror is epistemic, not apocalyptic. Our maps feel complete because the inner system is bright and fast, and brightness makes discovery feel inevitable. The outer system is dim and slow, and that slowness is a hiding place. Objects barely move, and their photons arrive reluctantly. The universe can conceal large objects in plain sight, because our instruments are finite and our attention is biased. What else have we mistaken for absence simply because it is inconvenient to detect? This is the deeper theme of the documentary, and the visuals can linger here. A wide shot shows the planets close to the Sun, then the camera pulls back until they become a tight cluster. The Kuiper belt appears as a faint torus, then fades into a sparse halo. Beyond it, the screen is mostly black, but the black is not empty, it is underexposed. The edge of the solar system is not empty, it is a living archive of gravity. Every detached orbit is a fossil of past encounters and long talks, carved by resonances, scattering, and the tidal field of the galaxy. Every new detection is a new constraint on what the Sun has been carrying, and constraints are the currency of this science. The archive is not written in rock layers, it is written in orbital elements. When we read it correctly, we read time. Akari's whisper belongs in this synthesis as a disciplined uncertainty. If the candidates are real, they should move, and motion will settle the question more cleanly than argument ever could. If they are not real, their failure still teaches calibration humility, because the infrared sky is crowded with deceptive structures. Either way, infrared remains essential, because a cold planet should have a thermal budget, and thermal emission does not care about reflected sunlight alone. A cold planet's temperature is set by a balance of absorbed sunlight and emitted infrared, modified by albedo and any residual internal heat. At hundreds of AU, sunlight is weak, but not zero, and an object with a large radius still intercepts a measurable trickle. If the planet is massive, it may also retain heat from formation, leaking it slowly over billions of years. That is why infrared surveys matter. They are not just looking for light, they are looking for energy. KQ-14 also belongs here as a reminder of a leverage. One object can tighten a corridor, or it can expose a fragile pattern, because dynamics is sensitive to initial conditions when the system is weakly bound. Its refined arc will either integrate cleanly into a shepherded population, or it will widen the plausible histories by refusing to fit. The point is not KQ-14 alone, but what it forces models to explain. In science, a single stubborn datum can be more valuable than a dozen agreeable ones. The clustering thread belongs here as both clue and caution. If clustering persists in a bias-corrected Rubin sample, it becomes a gravitational fingerprint, the kind that points to a persistent perturber rather than a temporary coincidence. If it collapses, it becomes a fingerprint of our own observing habits, etched by telescope schedules and human priorities. In both cases, the outcome is a map of how knowledge is made, and that is a kind of resolution. The decisive tests are therefore procedural, not mystical. Repeated imaging must yield consistent motion and parallax for any candidate world, and the motion must match the slow rhythm expected at great distance. Orbit fitting must predict future positions that keep being correct, because prediction is where models earn their keep. Thermal measurements must match a plausible radius and temperature, if a planet is claimed, and the spectrum should be consistent with cold ices rather than a distant galaxy. For the PBH alternative, the decisive test is gravity acting on light. Microlensing must show a clean, symmetric event with parameters consistent with a nearby compact mass, and the inferred lens distance must make sense in the solar neighbourhood. Follow-up must fail to find a luminous counterpart at the lens position, even with deep imaging that would reveal a faint planet. Dynamics must remain consistent with a point mass perturber across the growing ethno-catalogue, because a PBH would behave like mass concentrated into almost nothing. Rubin does not work alone in this ending, and that matters for credibility. Rubin provides discovery and cadence, then follow-up telescopes provide characterization, including spectroscopy and deeper imaging in multiple bands. Infrared archives provide backward time baselines and thermal constraints, letting astronomers ask whether a candidate was present years ago in a different survey. Independent teams provide replication, which is how claims become durable, and durability is what separates a headline from a result. The 2025 survey era is the turning point because it changes the rhythm of the sky. Night after night, the same fields are watched until motion separates from background, and the separation becomes a track. The search stops being a heroic guess and becomes an audited program where non-detections are as informative as detections. The pattern either breaks or the culprit steps out of the dark. There is a quiet philosophical shift embedded in that rhythm. When the cadence is regular, the sky stops being a place you visit and becomes a place you monitor. Monitoring turns uncertainty into a curve that narrows, because each revisit rules out more of the parameter space. Even if Planet 9 is not there, the act of looking with discipline changes what we can responsibly claim. What does it mean to be confident, when confidence is earned one night at a time? If Planet 9 appears, the signal becomes a world with coordinates, mass, and a history, and the corridor becomes a destination. If it does not, the outer solar system still becomes clearer, because bias is measured and populations are mapped, and the archive gains new pages. If the PBH gains ground, the solar system becomes a bridge to cosmology, and the word neighbour changes meaning, because our neighbourhood would include an object older than the Sun. This chapter closes without pretending the universe owes us a familiar answer. The hunt has already revealed something true about our situation, regardless of which branch wins. We live inside a system whose outskirts are still being inventoried, and inventory is not a metaphor but a workflow. Our certainty is local, and our ignorance begins where light fades. Whatever Planet 9 is, or is not, the method is the message. Science navigates mystery by turning faint signals into testable predictions, and by letting those predictions face time. It turns time into evidence, and evidence into a new map, even when the map redraws what we thought we knew. At the edge, the map is provisional, and that is why the story remains unsettling. We followed a faint infrared whisper into a region where distance itself becomes camouflage, and where the Kuiper belt turns into a statistical trap. We watched a handful of extreme trans-Neptunian orbits, including the Uneasy Witness 2023 KQ-14, hint at long-term shepherding while reminding us how easily surveys can manufacture patterns. We sifted Akari's cold point candidates through cirrus, galaxies, and artifacts, then arrived at a new era where Rubin's cadence turns hints into auditable motion and biases into measured selection functions. Across every chapter, one idea kept tightening like a knot. The edge of the solar system is not empty. It is a living archive of gravity. The orbits out there keep records for millions of years, but we only glimpse them during brief bright arcs, and we mistake that geometry for truth. A planet would leave a thermal body to find, a spectrum to measure, and a parallax loop to trace across seasons. A primordial black hole would leave almost nothing to photograph, yet it could still write the same orbital handwriting and force us to prove a world by its absence. That is why the hunt has shifted from romance to metrology, from single images to time, and from anecdotes to catalogues that can be interrogated. Rubin will grow the sample from dozens to thousands, test whether clustering survives bias correction, and map resonant islands or dissolve them into noise. Rubin will also watch for microlensing curves that do not care about albedo, temperature or atmosphere, only mass passing in front of distant starlight. If the infrared whisper is real, it will move, it will repeat, and it will cross-match, because the sky can hide a world, but it cannot hide motion forever. We are left with 3 honest branches, a directly imaged Planet 9, a pattern that collapses under quantified selection effects, or a gravity-only culprit consistent with a compact dark object. Each branch has a different kind of ending, and none of them is comfortable. A planet reshapes our story of formation, migration, and what the sun could keep. A statistical mirage reshapes our story of how easily we fool ourselves at the limits of detection. A primordial black hole reshapes the story most of all, because it would be a relic older than the sun, parked in our backyard, and discovered not by light, but by the way it bends time and trajectories. So, are we finally hearing a secret planet, or the signature of something far worse in that exact patch of darkness beyond Neptune? The most truthful answer, for now, is that we're hearing gravity first, and learning what kind of object can speak in that language. If the whisper becomes a trackable source with parallax and thermal consistency, it is a world we can name. If the orbits stay organised while the sky stays dark, then we may have to accept that the thing rewriting the frontier is not a planet at all, but a compact mass that refuses to shine. In the end, the horror was never that something out there might come for us. It was that our map ends where the evidence begins. The frontier beyond Neptune is not a void, it is a ledger, and in the Rubin era the ledger will balance, either with a new planet on the last page, or with a deeper question written in the ink of invisible mass. As Rubin's first seasons arrive, follow the data as closely as the headlines, because the next proof may be an orbit closing, or a microlensing curve rising and fading in silence.